well, why don't we get started? I'm very excited that we have Colin Adams kicking off this great session on open and accessible problems for undergraduate research that's hosted by the Sigma on Undergraduate Research. By the way, the Sigma is looking for new leadership. So if you're interested in getting involved in the Sigma on Undergraduate Research, please consider coming to our business meeting on Saturday morning, where Colin's colleague, Pamela Harris, is going to be giving a talk for us as well. But thank you. Without further ado, I would love to hear from Colin Adams about knotted undergraduate research, multi-crossings, and pedal numbers for knots.
Great. Thanks, Allison, and thanks very much for organizing this session. It looks really fun. So I'm going to tell you about some ideas from knot theory, and I realize the audience is a mixed audience, some people who spend a lot of time thinking about knots and some people who haven't spent any time thinking about knots. So I will at the end talk about some kind of books that are of a more elementary nature for anybody who's interested, but I won't be assuming any particular background in knot theory. So typically when people draw pictures of knots, they look like this, and you see this is the beginning of the table of knots. Any two of these knots in this picture, one cannot be deformed to look like any other. And the important idea here is that we represent a knot by one of these pictures where we have these crossings, where we have one strand crossing over another strand. These crossings, which I will eventually be calling double crossings, where one strand crosses over under another strand. And we have these set of moves that you can use to get from any one picture diagram of a knot to any other, which are called the Reitemeister moves, dating back to Reitemeister and Alexander and Briggs back in the 1920s, where you can change a diagram of a knot by adding in a little twist or putting a little two crossings in like this, or moving a strand in a triple crossing up and down. And Reitemeister moves will not change the knot, just the diagram of the knot. And any two projections of the same knot are related through a sequence of these Reitemeister moves. So about a decade ago now, I was teaching a course on graph theory, and I was looking for papers that I thought were readable for the undergraduates, and I stumbled across this paper on the archive called Triple Crossing Numbers of Graphs due to Tanaka and Teragato. And Tanaka and Teragato are graph theorists, and they were interested in the question that graph theorists are always interested in, which is, if you want to draw your graph, some graph that somebody's handed you in the plane, how can you do it so that the number of crossings generated by edges crossing each other is minimal? So in other words, here's the Peterson graph, and you'll notice when I try to draw it, it's an abstract graph, but if I try to draw it in the plane, it's not a planar graph, which means I have to have these points where two edges intersect. And it turns out that for this particular graph, the crossing number is 2, meaning the least number of crossings you can generate is 2 crossings, as in this picture here. Now, what Tanaka and Teragato noticed is you could take this edge right here and pull it around the other way, and instead of having 2 double crossings, you have a single triple crossing. So you only have a single place where you have any edges crossing each other, but you allow 3 edges to cross at that particular point. And so this, I thought this was really interesting when I thought it. And then immediately when I saw this, I immediately thought, well, wait a minute, could you do this for knots? And so that's what we're going to be talking about today, is we're going to talk about extending this idea to knots. And we're going to define a triple crossing in a knot diagram to be a place where 3 strands cross each other, each one bisecting the crossing. So you can't come in and bounce off. You have to go straight through. And I'm going to label them with a T for top, M for middle, and B for bottom. And what that means is if I slide the strands off each other a little bit, it would look like this. So that single triple crossing would resolve into 3 double crossings, but you'll notice this triangle here is not alternating. I have one strand that's going over everything and one strand that's going under everything, and then one strand in the middle. So this is what I call a TMB crossing. We'll come back to that idea in a second. And so you'd like to know, is it true that every knot has a projection with only triple crossings? And if I have a projection with only triple crossings, I'll call it a triple crossing projection. So let's look at a couple of examples, 2 very famous knots, the trefoil knot and the figure-8 knot. And I'd like to find triple crossing projections for these knots. And if I do so, it turns out they look like this. And so you'll see for the trefoil knot and the figure-8 knot, they have the exact same diagram. They have the exact same diagram The only difference is the labelings on the crossings. So down here, this crossing that you see right here, if I move the B up here, this is what I would call a BMT crossing. This one, if I move the B up here, because the B is the same on both sides, this would be a BMT crossing. This one is a TMB crossing, whereas this one is a BMT. So they differ in the type of crossing.
Just so you know, we can't see your cursor.
Oh, that's good to know. Thank you very much. Thank you. That helps. Thank you, Allison. I appreciate that. Okay, so the top crossing is different between the two. The labelings on the top crossings are different. Now, just to remember, I always use this memory device for my two types of crossings. So TMB crossing, I think of as Texas Medical Board, and BMT, basal metabolic temperature. Okay, so we have two different types of triple crossings that you can have. Okay, so now I'd like to know whether or not every knot has a triple crossing projection, and I'm going to use this idea of a collection of crossing covering circles, which will allow me to obtain a triple crossing projection. So you see here on the left, sorry, I keep touching this and then it switches. So you see here on the left, a projection where I've drawn I have three crossings, and I have a circle that passes through all three crossings and bisects each of those crossings. And that's going to be a crossing covering circle, and it doesn't touch the knot anywhere else. Now you can imagine a knot projection where I have a set of these circles all disjoint and covering all the crossings. Now, given a crossing covering circle like that, I'm going to take one of the overstrands and one of the crossings, which you see highlighted in yellow here, and I'm going to, instead of just allowing it to pass straight over the crossing, I'm going to deform it to go around the crossing covering circle, going over anything, and then coming back to the other side. And what that does is it eliminates the one crossing that I started with, and it turns the other crossings on the crossing covering circle into triple crossings. And I'm going to call that a folding. So if I have a collection of these crossing covering circles that hits every crossing, I could fold each one, and the end result would be a projection with only triple crossings in it. So let's prove that every knot has a triple crossing projection. I know of three proofs of this. One was the first one I came up with. This is going to be the simplest one, but the very first one that anybody ever did was actually due to Von Jones, and I was at a conference and talked about this, and Von said afterward, you know, I proved this back, 10 years ago, and in a paper that's on the archive, and that paper's never actually been published. It's still on the archive. It never did get published, but it has over 500 citations, so it's actually a very important paper. But anyway, so here's a very simple proof of the fact that every knot has a triple crossing projection. We're going to use Alexander's theorem, which says that every knot can be put in a braid presentation. So a braid being here, going from here to here, where each of the strands goes left to right and monotonically moves left to right, each of the strands that we see here, and then I connect the bottom to the top around the outside. So that's a braid presentation for a knot. And you'll notice that if I have a braid presentation, it's very easy to come up with a covering crossing collection of circles that will pass through all the crossings. And this one, I just need two such circles that passes through every crossing. So I have an obvious collection of crossing covering circles, and therefore I can fold along them and I will get a triple crossing projection of the knot. So that means I can define the triple crossing number of a knot, which I'll denote C sub 3, to be the least number of triple crossings in a triple crossing projection of the knot. And so in the example of the trefoil knot in the figure 8, we found diagrams that had 2 triple crossings for each of them, and you can't do them with 1 triple crossing, so in fact their triple crossing numbers are both 2. In fact, you can prove that every diagram of a knot has a covering crossing collection of circles, which means that the triple crossing number will be less than or equal to the crossing number minus 1, because there'll always be at least 1 crossing covering circle. And when you fold it, you will lose a crossing and turn the other crossings into triple crossings. So that's a fact. And you'd like to ask the question, well, what knots could generate that upper bound, where the triple crossing number is just 1 less than the crossing number? And in fact, you see a diagram here which has just a single crossing covering circle, and that's what you need for it to be true. So if any knot other than a 2 braid, as you see in this picture here, any other knot, the triple crossing number will be less than or equal to the crossing number minus 2. You like to know that the triple crossing number for the 2 braids is crossing number minus 1, but that's open. And that's been open for a while. So anybody interested in that question, that would be really interesting to be able to prove that in fact the triple crossing number for 2 braids is crossing number minus 1. In this diagram here, where you see a single crossing covering circle, it would generate a diagram with triple crossing number equal to crossing number -1, but you don't know that there might be another way to generate a diagram with fewer triple crossings. So that was the upper bound on triple crossing number. What about a lower bound? Well, given any triple crossing, you can always expand it into 3 double crossings, as we saw before, resolve it, and therefore the crossing number, or what I've been calling the double crossing number, is less than or equal to 3 times the triple crossing number. So in particular, triple crossing number is always greater than or equal to crossing number over 3. So then you like to ask the question, do there exist knots such that the triple crossing number realizes this lower bound? And this was work from SMALL 2013. Now, SMALL is the summer research program funded by the NSF at Williams College. And I had a group working with me that summer, and we found this particular knot here, which is a 12 crossing knot. And in this picture, you can see the resolved triple crossing. So these 4 places where you see these little triangles, and that is, each of those actually is a valid triple crossing when you pull them together. And so the triple crossing number turns out to be 4 in that particular example. But it's an open question. This is another open question that I hope someone will pursue at some point. Classify the knots such that they realize this lower bound, such that their triple crossing number is equal to crossing number over 3. That would be a very interesting problem for somebody to solve. All right, so now let's look at higher order multi-crossing. So instead of just having 3 strands pass through a crossing, of course, the next question you might ask is, what if I had 4 strands passing through a crossing? Now, instead of using T, M, and B, I'm just going to use integers now, labeling the strands passing through the crossing. So the strand labeled with 1 will be the highest strand, then 2 will be the next highest, 3 will be the third highest, and 4 will be the fourth highest for my in this case, a quadruple crossing. And if I want to show that every knot has a quadruple crossing, I can use the following trick. Take your standard double crossing projection, and then just take that understrand at each crossing and do this loop-de-loop that you see right there with the extra loops on it. And in fact, at the center of that, you actually do have a valid quadruple crossing together with some loops hanging off it, but it still is a valid quadruple crossing. And therefore, that means since every knot has a quadruple crossing projection, you can define the quadruple crossing number to be the minimal quadruple crossing number over all quadruple crossing projections of the knot. The one difference here is there are more different types of quadruple crossings. So you'll remember in the case of double crossings, we had TMB and BMT, there were 2. But now, in fact, there are 6 different quadruple crossings. And interestingly enough, actually, they have different properties. So for instance, if you look at hyperbolic volume, the volume contribution from different types of quadruple crossings actually varies depending on which quadruple crossing it is. Let's ask the more general question. Is it true that every knot has an n crossing projection for all n greater than or equal to 2? And I'm going to use the same trick when n is even. Namely, I'm just going to take the under crossing and I'm going to do the loop-de-loop, only I'm going to have a couple extra loops in it, and that will work to show that it has an n crossing projection for every even n. That actually is easier than the case of the triple crossing, by the way. But when n is odd, what I'm going to do is I'm going to first turn it into a triple crossing projection using that folding that we showed before, and then I'm going to use this trick to get any odd n. So the answer is yes, it does turn out that every knot has an n crossing projection for every n, and therefore a minimal n crossing number. So now, instead of 1 crossing number, the traditional C sub 2, which is the crossing number of a knot, we now have a spectrum of crossing numbers. So for example, the one we saw before, the trefoil, its double crossing number, which was its traditional classical crossing number, is 3. Its triple crossing number is 2, and its quadruple crossing number is 1. And then after that, C sub 5, C sub 6, etc., they all stay at 1. And so it just has that single crossing in the center on that last one, and we will come back to that in just a little bit. So this was the small group from 2013. All of these students went to graduate school at the schools that you see there. Most, but not all of them are done. I think almost all of them are done, but not quite every one of them is done at this point. And they, working with me, came up with a table of these multi-crossing numbers. So on the left-hand side, you see a list of the knots. And then on the top, you see a list of the known multi-crossing numbers. Now, you'll also notice a lot of gaps in the table. And so you'll notice also the symbols that we put by each number, which tells the method we use to determine that number. But you'll see the very first opening is under the knot 7-1. The second entry is C sub 3. That is the triple crossing number of the 2 braid with 7 crossings. As I mentioned, we do not know the triple crossing number of the 2 braids. And so that's the very first opening in this table where we don't know the answer. I'm just going to look at the top part of this table a little bit closer. So here's the first 1, 2, 3, 4, 5, 6, 7, 8, 9 knots, 8 knots. And I just want to point out, you might hope that the spectrum of values would completely determine your knot, but it does not. As you see, the last 3 knots in the table all have the same sequence of multi-crossing numbers. So what other ideas from knot theory generalize to n-crossing projections? Well, what about braids? So you'll remember, as I mentioned, Alexander proved every knot or link can be put into braid form. So here is an example of what I'm going to call a 2-crossing braid, because all of the crossings are 2 crossings, crossings with 2 strands. Could I have a 3-crossing braid? So every one of the crossings that appears in the braid has 3 strands passing through it. And Daniel Vitex, who was on the left in that last picture I showed you, asked this question. For a given fixed n, does every knot and link have an n-crossing braid projection? Can you use this idea for knots and links? And so my thesis student, undergraduate thesis student, Daishiro Nishida, decided to think about that question. And the answer is no in general, and Daniel knew this fact. Namely, if n is odd, then no knot can be realized with an n-crossing braid. And the reason for that is you could just label your strings odd and even, and when you pass through an odd crossing, it doesn't change the fact that certain strands are labeled with odd and even. So it preserves the odds and evens, which means when you're done with your braid, you will have a collection of loops that are all labeled E and a collection of loops that are all labeled O, and never the 2 shall meet. So you must have at least 2 crossings. But then Daishiro and I are writing a paper which has not yet appeared, which proves for every even n, every knot and link has an n-crossing braid projection. And for every odd n, every multiple component link has an n-crossing braid projection. So in particular, that means that we have a spectrum of braid indices, just the even ones for a knot and both even and odd for the links. And it is an open question to find the higher order braid indices for any knot or link. Now, what I mean by that is no one has figured out the sequence of these numbers for any individual knot or link. And I don't think it would be that difficult to do that. It's just I haven't done it, haven't had time to do it, and nobody else has had time to do it. So I think that would be an interesting question to try to determine some of these numbers for various knots or links. Okay, here's another question I want to ask. I showed you this projection before. Does every knot have a projection with a single n crossing for some n greater than or equal to 4? And we'll call that, this was the students who picked this name, an Uber crossing projection. It's a projection with a single n crossing. And here's a very particular type of Uber crossing projection called a petal projection, where none of the loops are nested. And so you get this thing that looks very much like a flower. The numbers on these strands correspond to the height they're passing through the single central axis. And this is small 2012. This is where these students went to graduate school. I think at this point, all of them are actually finished. And very strong group also. And together with me and Tom Crawford, who wasn't in that picture, we proved every knot has a petal projection. So every single knot has a projection, and therefore you can define the petal number of a knot, which is the least number of loops in a petal projection. So here is a 3D printed knot that looks quite ugly from the side view, but from the top view, actually, you can see that it's a petal projection. And so then we made a table of petal numbers and the permutations that correspond to the petal numbers. And various people have followed up on this. So Mark Hughes, working with three undergraduates, came up with Reidemeister moves for petal diagrams. So any 2 petal diagrams of a given knot are related through a sequence of 2 possible types of Reidemeister moves. Chaim Even Zohar, Joel Haas, Nadi Lineal, and Tal Noack used these petal diagrams in what they called the Petaluma model, because they came up with it when they were in Petaluma, to generate random knots. So you generate just random permutations, and that is generating random knots. So it's a very easy way to generate random permutations. Allison, who's organizing this session together with Robin Truax, used petal projections to determine an algorithm for calculating p-colorability and determinants of knots from their petal diagrams. And so really the idea here is you take your favorite idea from knot theory and extend it to these petal diagrams, Uber-crossing diagrams, and multi-crossing diagrams. And finally, the last one I'll just mention real quick, Lou Kaufman invented the idea of virtual knots. This is my favorite picture of Lou Kaufman. And virtual knots are just like regular knots, but they have these additional virtual crossings with the little circles on them. And in a very recent paper, students and I, this is a set of students, one Professor Chaim Even Zohar, and the rest were students from my knot theory class, extended multi-crossings to virtual knots. And in this paper, we have a whole slew of open questions at the end of that paper that would be wonderful to see people to pursue. So some final questions real quick. How can we recognize the unknot from its petal permutation? So that's an example. This happens to be a petal permutation for the trivial knot, but how do you tell that? Are there certain categories of knots that come out of this viewpoint? It seems like n-1 torus knots play a very important role here, but there would be other categories. Every knot has a n-crossing number of 1. Is it true that the n-crossing numbers are non-increasing? And what we know is that the even ones are non-increasing and the odd ones are non-increasing, but we do not know that altogether they are non-increasing. How is the span of the bracket polynomial related to Uber-crossing number and petal number? How are the knot homologies related to all of these quantities? And then finally, I won't go through this because I know I'm out of time, but generalize whatever your favorite idea is that applies to double-crossing projections to higher n-crossing number or Uber-crossing number or petal number. So pick your favorite thing and generalize it. And I'll just mention, these are, for anybody who hasn't seen knot theory before, these are 2 books, one by Allison together with Inga Johnson, which is a great introduction to knot theory. And then this is another one that I wrote, which is also an introduction to knot theory. There are many other great books, although most are at a higher level than these 2. And no animals were harmed in the production of this talk. And if you want references, if you just go to the archive and type in my name, you'll see a lot of papers that are related to this. And I will stop there.
Hooray! Thanks, Colin.
Thank you. You're welcome.
This was wonderful. So if anyone has questions, right next to the chat, there's a place where you can click on Q&A, and you're welcome to type a question in there, and I'll make sure that Colin sees it.
Thank you.
Yeah, so everyone's saying thank you. I know you probably can't see the chat, or can you see the chat now, Colin?
Yes, I can see now, yes.
Okay,
actually.
great.
Yeah.
Cool. So any questions for Colin? Okay, we have one. Maybe you can see this too. So Anthony Bozeman says, can you share a bit about how you, as an advisor, know when a problem is a good problem to give to undergrads or not? How much do you play around with it a bit yourself before to see if it's good?
Yeah, no, I mean, that's a great question. And it's something that I think when I started doing research with students, I wasn't as good at, and I've gotten better at it over the time. And, you know, one thing that's always true is I always have my antenna up for good problems for undergraduates. Every talk I go to, everything I see, I think, could this be a good problem for undergraduates? And to me, the best kind of problem for an undergraduate is one where they can start playing with it right away. So they can start drawing pictures, they can start doing calculations, they can start seeing results, if you try to do these things. And then ultimately, maybe they're going to try to prove the big result, but in the process, they get sucked in by working on particular examples. And so ideally, that's what you would like. So to me, that's really kind of the key to finding a good problem. And then do I play with it? Yeah, I do. I mean, beforehand, I kind of play around and I think, is this reasonable? Is it not? Now, the truth is, usually I'm doing this in our summer research program. And the truth is the problem we ultimately solve is ultimately not the problem that I gave them to solve, right? We work on that problem, we come up with other things, we realize we're against a wall on that thing, but these other directions go. And so that's another part of this, is don't be too committed to the one you set out to prove. There's lots of other stuff that you stumble across in the process.
All right, great. So I see that Moira is trying to get up here. So maybe we'll just take one more question. So if Luke Barbarita asks a question, what broader math fields would be beneficial when getting into knot theory?
So, I mean, the other areas that play an important role in knot theory, I mean, certainly topology, combinatorics, I think those both, depending on what kind of knot theory you do, geometry, I do a lot of hyperbolic knot theory, which requires a lot of geometry. But the most important two, I would say, are really, and also algebra, certainly. If you get into things like quandules, algebra is very helpful. But topology is kind of the most. But, a lot of the problems, really, you don't need a lot of background. You do not need heavy duty topology to do a lot of knot theory. So a lot of the problems are simple and of a combinatorial nature that you can approach them without having a huge background.
Great. Well, let's thank Colin again. Thank you so much for being willing to give a talk in our session. As always, it's wonderful hearing about multi-crossing projections. And maybe you and Jeffrey can talk about his question offline that we didn't get to. But for now, I'm going to invite Moira Chass up to get ready for her talk. Thank you, Colin.
No, but I'm early. I just asked before because I'm kind of anxious, but
Yeah. Well, we want to make sure you can share your screen and everything before your talk begins. Colin, do you know how to stop?
Yeah, I think I can stop myself. Goodbye. And thanks everybody for listening.
Thanks.
So let me see if I can share. Let's see. Oh, yeah.
Oh, yeah. Great. That looks great.
And appears in the screen. Yesterday I gave a talk and I don't know why it didn't appear in the screen, which was very weird.
Oh, no.
Same setting and everything. But anyway, we're good now.
Well, this is great. Okay. So we have a couple minutes. Do you have any questions for me? It seems like you can't point at things, unfortunately.
Oh, let me try to point. Let me see. I have a Mac.
Yeah. Oh, yeah. Okay. Yeah, we can see that. Great.
Okay. Good.
Colin, I'm not sure why we couldn't see your cursor. That's very strange. But maybe it is a Mac issue.
Well, I don't know. As I said, I gave a talk yesterday, exactly the same setting, but I couldn't see. Oh, no. I think I know. I was projecting something. I couldn't see the projection. Maybe anyway. I don't know.
Gotcha.
I don't know if the things are logical, but I can answer. Because we have 2 minutes. I can answer the question that was asked to Colin about. What type of problems and what you do. What type of problems do I choose? And you will see that many of the problems I had involve some experiment, which often is a computer experiment. You just study many cases of something. And then the idea is, if you can do, in certain cases, a good enough study and have a good enough conjecture, that's already something. I totally agree with Colin that it's nice to have problems that you can start thinking about right away. I mean, for me, and I think this is happening to me now, is that it's great when a problem pushes you to learn the math, as opposed to you learn the math to understand the problem. No, I want to, I function the other way around, and so that's another thing. And the third thing related to that is right now there's another session, the one I gave a talk yesterday, amateur mathematicians. And you see what is this enormous persistence, that somebody who gets some question for some reason, it starts burning inside you and you think and think and think. And usually when you put enough time and energy, something happens. I'm not saying you're going to find the answer, but you're going to grow in understanding. So in some sense, I try to face math, and my students and everybody face math with that, amateur mathematician spirit. Let's understand something.
Well, thanks for answering that question before you even get started. It's now time for the start of your talk, so I'm very happy to introduce you. We're very fortunate to have you speaking in our session. And this is an exciting topic, computer-driven questions and theorems in low-dimensional topology. So without further ado, from Stony Brook, Moira Chass. Thank you.
So hi, it's really a great pleasure to be here. I want to announce, I just, on purpose, I'm not going to look at the chat just because my mind works in one direction. And if I read the chat and talk, I cannot think about what I talk about. So I'd rather think, and then somebody can put volume and ask if you need a question. I don't mind if you interrupt for asking, but I wanted to be aware. And I took some time in preparing this first title slide, which just realized there's not my name there, but it's fine. And these are some of the students I work with and some of the topics, we or they thought about. And it was so happy to prepare this and remember all these moments. And, in this period of our lives, I mean, I take any happiness that I can get. So it was really nice to do one by one and try to find pictures and putting them there. Here is another picture. This is in Stony Brook in the common room, which I hadn't put a foot there for a long time, as you can imagine. And here you see, well, in the summers, I do a workshop where it's quite open and everybody can come and, you have to earn the right to work on a problem. So this is, I mean, sometimes we have a review, but in general, my system is people come to want to learn, and I have little problems to learn and small problems. And when you show your investment in this, you earn a problem. And so let me start with a little bit of the mathematical setting of what I'm going to talk about, so we can you can understand the problems I'm going to discuss. And I'm going to assume almost zero from everybody else. Okay, so surfaces. So here are examples of surfaces. And when I say surface, of course, I mean like the outer layer of these shapes, and remember that two surfaces we consider equivalent. We can say if we can deform one into the other without tearing them, or they are homeomorphic, if you understand that word. And here I have other kind of surfaces. And if you had more time, I will stop and ask you, but 20 minutes is too short. So this surface have boundary. So here you see, for instance, this edge here is a boundary, as opposed to the previous one we didn't. And I'll tell you why surfaces with boundary are going to be really good for our purposes. And I'm going to think about orientable surfaces. This is a Klein bottle, which is a non-orientable. Remember, orientable, we can think of, it doesn't contain a Möbius band. And almost when I say surface, I will mean orientable. So right now I'm going to encode surfaces. And the way I'm going to encode it, I'm going to describe it with an example. So here I have a pair of pants. They're both versions of a pair of pants. This one is a pair of pants for a person with a very strange and unusual body. And here, we can imagine you expand the waist and you stretch it, and you manage to put it on the floor. Having it flat sometimes hurts to study curves on surfaces, which we're going to do. But it's not likely that you will be able to make your surface flat. So to study the surface in general, what I'm going to do is cut the surface. And I'm going to cut it by going from one boundary to another. This is a cut, just a straight line. The cuts are not supposed to intersect each other, and they can go from a boundary component to another, but they are not allowed to separate the surface. So I do one cut, I look, oh, this is my surface flat and a polygon? No, I keep cutting. So here, my pair of pants, I made two cuts and I open up, and then I transform it into a polygon with a memory of whom it was glued to whom in the original surface. Very important. And you see that to keep the memory, well, we can have the colors, and I put letters, and the letters have uppercase and lowercase. Right now, the letters are just function like the colors, and I could have lower uppercase, it doesn't matter. A little later, the letters will play a role, so don't get hung on this now. So then I'm going to just copy. I'm going around and copy the letters I wrote, and this is a surface word. So it's a ring of letters. and you can clearly, get the rules of the surface letter. If I have a lowercase, I have to an uppercase, and vice versa. There are finally many. There's an even number, etc. So let's do with another surface. This is a torus with a boundary component, and I'm going to cut it. And now, since we're more expert in this, I'll do it faster. And I open up. Again, this is torus with one. So the boundary in this case was divided into 4 pieces. Since I have only one boundary component, all the cuts start and end there. And I don't know if I said it clearly, but the cuts cannot separate the surface. So this is the surface word. So here we have the surface word of the pair of pants. It's A, B, B. This, and with corresponding capitalization, the surface words of the torus is A, B, capital A, capital B. So they are 2 different. And you might ask, well, is it true that two different surfaces have different surface word? And the answer is super yes, because knowing the procedure to getting the surface word, I can always go back and it's the same. But it might be that the cuts, I have made choices when I do the cuts. Not in this case, it's of very simple surfaces. If I make choice, one surface can have 2 different surface words, but we're going to usually fix the surface word. And so let's look at now curves on surfaces. So let me remind you, we think of a curve, it's just like a rubber band, very, very thin, wrapping around the surface, never allowed to leave it. The examples I have here, have no crossings, but they may have crossings. I like it. I borrowed this picture, and I like the rubber bands, image. And we're going to study curves up to deformation or homotopy. So the curve can move in the surface. This is a very primitive animation that I made, but here it is. And all these curves are in the same class because they can all form one into the other. And since this is topology, we'll be interested in studying the class of deformation, not just the single curve. Another way is to imagine that you can map, sorry, this thing is bothering me, a cylinder. Well, I don't know how to take it off, but apologies. You map a cylinder to the surface, and one boundary component goes to one curve, the other boundary goes to the other curve, and that gives me a homotopy or a deformation of the curve. So now that we have the class of curves, we're going to fix the surface word. So we fix our surface, and we're going to encode the curves. So now the capitalization of the letters are going to play a role. Here we have A, B, B, and this curve here, the green curve, I'm going to label with a B. It's like a ring of letters, with a ring with only one letter, with a B. Same with the A. This letter here, this word here, I'm going to label with, I start here, let's do A, come around, then small b, come around, then capital A, and then capital B. Notice that I choose the capitalization with the side of the cut that I first hit. And then I get a curve word. So they have these 2 objects, curve words and surface words. And one more thing for the setting is curve words have to be reduced, meaning that they don't contain a lowercase and an uppercase together. So for instance, if my curve, the curve that I had before, I could have drawn it so I have a little tongue here coming and going back, but I always make my curves tight so they don't do that. Because what I want is one class, one curve. So let me skip this. Here I have another curve, but my time is pretty bad. So curves are going to be, I'm going to think always as ring of letters, even if sometimes I write them as a word, a linear word, because writing a ring of letters is very painful. So now the self-intersection number of a curve is the smallest number of crossings of a curve in a class. So the self-intersection of this, well, it's at least 1. I mean, maybe there's a way of deforming this curve that removes that crossing. No, there's not, but I'm not proving it. So, but you see, there's one member of the class that has 1 crossing. So therefore, the self-intersection of this class is 1. So now we're going to use the words to study the self-intersections. So I have this word this curve in the torus, And I'm going to study one point, this point intersection point here. And I'm asked myself, why is this point here? Well, because it's in this piece of curve and this piece of curve. And when I look at the word corresponding to this letter, to this curve, I see that, this goes from the small b to the big B. And you go to the small b to the big B edge when you have a capital B in your word, because then you enter through the capital B, go out here and enter again, and that gives you this segment. Same here. This is here because I have a small a. So every time I have this pair of subwords, AA, BB, I'll have an intersection. And in fact, this can be generalized, and I don't have time to go over there, but there's a one-to-one correspondence. If you have a curve that intersects itself with the smallest number possible of points in the class, then it's a one-to-one correspondence between each self-intersection point and each of these pairs that I call link pair. There are special pairs of words that depend on the surface word, and those can be defined by a computer. They are totally, combinatorially defined. So let me go a little fast because I see my time and it's terrible. I didn't speak about a problem. So given a curved word, we have the word length. This is the number of letters, the number of letters the word associated to this class has, and then the self-intersection number. And one thing one can do is study the relations between these numbers. So here is what I did. And this is many years ago. I made this table, and pay attention now if you're sleeping, because this is going to be important for a little bit. So in the column 1 and row 2, for instance, I put how many curves we have, words of 2 letters. So the number of the letters is given by the row, and the number of the self-intersection number is given by the column. And this is it. It's always, of course, in a fixed surface. And then I just program this and I put it in a computer, and this is the numbers you get, up to 8. And then you look at more. And when you see this table, I'm sure that you there on the other side of the screen can see that there are patterns here. There are a lot of theorems waiting to be proven. And many of those theorems, many of the problems, I work with students, or they work themselves. So here is what I did is I color this. The darker the color, except the black, which is 0, the darker the color is the more curves. So here is first what I did. I was trying to work on some problem related to this table, and I had to draw representatives. I have to draw members of a class that have the smallest number of crosses possible. And it's really hard if you have a complicated word. And then I asked a student to find the classes. And to do that, first you notice that how can you add intersection points to a curve? Well, one way is you have bigons. So here, this little thing here, this is a bigon, this blue thing, it's like a polygon with 2 sides. So we have to destroy bigons and to find this representative with smaller self-intersection. So Chris Aretines, who went then to CUNY, here is with CUNY grad school in the background, he created a program to find it. And his idea was like, well, if you have a bigon and you have the curve drawn in my polygon, what I'm going to do, this is a bigon here. This is the vertex of a bigon. I'm going to try to see if I can push with my finger and destroy this bigon. The curve enters through here and come back through here in the same color. Well, let's see how to do it. And then he expressed that combinatorially. And here, it's a little animation that he did of how this, he wrote a little paper about this, and this algorithm is really nice because now we have a way to find representatives. Here is one representative that he already found. These are the problem I work, but let me just explain first. So this is a row of the table self-intersection and word length. So this is all the words of 8 letters organized by self-intersection. So this tells me here, for instance, that there are 16 classes of curves that have, labeled by a word of 8 letters and have self-intersection 0 crossings. And then I made a histogram. Here, the histogram, you draw a rectangle with a high proportional to the number of curves we have there. And you can see the pattern there. Like the idea is always let's find for patterns. This is what we obsessively do in math. And of course, you start to do more and more rows, the longer they were. And this is, an incredibly Gaussian. This took some work. This was not an undergrad problem. Here I got together with a statistician in the University of Chicago, Steve Lally, and we did prove that, if you take a number large enough of letters and you look at the distribution of self-intersection, that approaches to a Gaussian more and more when the word length, the number of letters, goes to infinity. And we have, ways to find, the mean and the standard deviation, but let me skip that. But now I can ask the same question for intersection. And I look at now intersections, which say they're defined in an analogous way to self-intersections with a fixed word. And now I'm going to look at a table again. I'm going to count how many curves have of 2 letters intersect 3 times with this fixed word, the one I choose here. And I made a table, and this I worked with a high school student who was incredible. And she did prove that this distribution of intersection goes to a Gaussian. Now, if you look at this table, there are already more theorems to be proven or patterns to be seen. All these zeros, for instance, and the fact that, there are non-zeros except, here there's a block of non-zeros. It's a nice result that we have to understand at some point. Okay, now, another thing one can do is, we have the curve word as we had before, and then forget about this, it's a lot of jargon, but we have the self-intersection number, the word length, the number of letters, and also we can have a way of measuring the length. Colin mentioned hyperbolic geometry, and this is, in fact, we put a very nice way, a nice metric, a very nice way of measuring the length of the curve, a metric that gives you a constant negative curvature, which you can do in most or almost all surfaces with boundary. And so there are 3 numbers that we can find relations of. And what we did, and it's funny because we worked with this very young undergrad student, Kenneth Lee, and an emeritus professor, Bernie Maskett, and me in the middle. And what we did is we look at all the words of a certain length, and instead of computing self-intersections, as I did before, we computed the length. And what we did is we varied the metric, and we saw that, this seemed to get it, closer and closer to a Gaussian when the length goes to infinity. And the proof was a little above, our time and energies at that time. But later, 3 mathematicians, kind of recently, found the proof of this result and even generalized it. So this pattern that we saw was generalized. And I have 2 minutes, and I'm going to skip this problem. Sorry, I'm going to skip just because I want to talk about another kind of problem. This is, I'm kind of lying, but I want to mention this because this is the last thing we did before the pandemic, and it's very nice. So we change gears now. As if you're asleep, you can wake up. So suppose you have a sphere and you want to divide it into regions. These are regions that are blocked, simply connected is the math jargon, so that every pair of regions share a segment of boundary. So, well, you can divide it into 2, and here I have an example of this division. You can divide it into 3. These are 3 regions, the red, the green, and the blue. You can divide it into 4, and the 5 jump there. And if you think for a while, you probably know that you cannot divide it into 5. In the torus, the number of regions is 7. And this is a nice picture. And if you can see me, maybe I should get my 7-color torus. I'm a maker, so hopefully you can see. This is a torus divided into 7 regions. It's very nice and very symmetric. Little extra structure here. This is the maximum number of regions in which I can divide the torus, so that every pair of regions share a segment of boundary. And now what if I ask you for a genus 2 surfer or a double bagel? Well, the number is 8. And this is the first picture I saw. It's a complicated one. I replicated it there. There's a better idea by Susan Goldstein. She made a wonderful teapot doing that. I did it in crochet a little simpler. And then I have a student, there was this algorithm, a very old paper from Hefter, which described combinatorially how to do it. And I thought, well, maybe we can really find a way to understand, to make a nice map on the surface with 3 handles, a triple torus or genus 3 surface, so we can understand. So let's try to make something. And he programmed, and this is the map we got. I mean, it looks very nice. This, again, the colors are glued together, give a genus 3, but this is not understandable. And he kept together working during the summer with, he joined forces with these other 2 students. He had them working. And they found out a way of doing it. So this is here, what you see here is a torus after gluing. So here you see, if I glue the pink with the pink, the black with the black, and the gray with the gray, we will get a torus. Well, they discovered that if I put 3 holes here and I attach a gadget to these 3 holes, and this is the torus here, and this is the gadgets they attach, and you get a nice map, which is understandable for the genus 3. And then they did it for the genus 4, and I have quite a few. This is the genus 4 and 5 and 6. And well, they have some other maps they're working, and they're finishing the paper. This is for you. You have a nice formula for the maximum number of regions. We know the proof is abstract, that this is the maximum number of countries you can put, but the maps are not understandable. And let me go to my very end. I can find I have a the end. Okay, so maybe here it is. This is one more thing. This is another student who made this nice program to study hyperbolic geometry. And since I'm overdue 2 minutes, I'm going to be shameless and advertise. I just put up a movie on YouTube about a wonderful mathematician, Alicia Bull. It's fictional, but it's based on facts, and you can Google it and tell me what you think about it. Okay, I'm done. Sorry for going.
Hooray! No, this is great. And actually, I don't see our next speaker in the session yet. So
Okay.
we might not be too pressed for time. So are there any questions for Moira? Fantastic talk, by the way. I love how there's statistics, there's combinatorics, there's topology, so many overlapping subjects we're seeing here.
Right. So yeah, I here is the idea is you have neat crochet. Well, yes, I have. Well, I have for the torus. I wrote a paper. No, it's an online note in the AMS site. I think it's called Crochet Topology. As you see, all these here are the maps that I did. In fact, in the AMS site, there's also the Klein model, which is somewhere else in 6 colors. So the torus map is there, and it's not hard to make. The torus is in this one. These are rectangles. I'm going to stop sharing so you can see maybe if I know how to stop sharing. How do I stop sharing? Oh, here.
You see a little.
I did.
Oh, okay, great.
So here is what you see here. This is the torus, and the rectangle. Well, there are 7 rectangles. More or less, the proportion is 1 to 4. 1 the short length, and 4 or 5 the long length of the rectangle. And this, I'm trying to see myself to see what you see, but this thing is anyway. And then you see the rectangle starts here and goes around, and ends here. So you make like a cylinder, and then you have to twist it and glue it. But I explain it in that paper. And what you see is that, for instance, this rectangle touches these 2 rectangles, so touches 2, there are 7. If I go on the extreme, touches other 2 colors, so here we have 4 colors. And if I go on the other side of the rectangle, it touches the last 2. So this is 2 plus 2 plus 2, as you well know, is 6, and it touches then the 6 colors. Yes, I did. I have Klein bottle. I have the Klein bottle and the Mevius band. Here is the Mevius band. Right now, I'm in a fury of working, so there are going to be more things soon coming up. But here I have a Mevius band which has 6 colors. And everybody should do this. It's really a good exercise to find a way to do it. I mean, for me, a problem, as I said, is really an excuse to learn math. And that's it. I'm more obsessed with 4D. Oh, speaking about knots, that Colin is there. So here we have, this is the ciphers of the trefoil knot.
Did you make that?
Yeah,
wow.
With these hands here.
That's amazing.
And you see, this one you can see is orientable and, think why. Oh, and I can advertise more. Gee, I'm very shameless today, but I'm giving a talk about these crochet toys on Saturday.
What session is that in?
The AWM Math in Action. Yes. I have to. My daughter created an Instagram account for me, and I have like 6 pictures.
Okay, so I am just emailing with our next speaker who is not registered for MathFest and so is not yet in the system. So I'm a little bit distracted by that. But let's thank Moira again, and feel free to ask questions and keep chatting while we kind of figure out what's going on with Kumar.
I'm here. I can show you more stuff.
Great. Thank you so much, Moira. This is so cool.
I can give pieces of the talk that I didn't give, so no worries. Any question? This is so weird that people can't talk. I mean,
let's see if we see any questions. Just a lot of compliments on how beautiful your artwork is.
Yeah, no, I'm reading now. Now I can read when I'm not. I'm going to put in the chat. Let's see. Well, if you Google Moira Chas, there's not many Moira Chas. Moira Chas, AMS, crochet topology. Yeah, here it is. So this is when I wrote the pattern for the torus, which is very relaxed. You sew the pieces. Oh, then I made I can show to the people who ask. I made 2 more tori. And these are, this one was the first, didn't come out too well, but this is, I just crocheted it all together. I crocheted in the round, the 3 colors, the colors all together, and there it is. I have to make one that, this is too fat and this is too thin, so I have to make one in the middle. But these are very new.
That's wonderful.
So these are great things to interacting with undergraduates and people. Everybody can understand when you touch and do. And students made for me, and this is another thing about map coloring. So this is a 7-color map on a torus. It's a famous one, but it's made with surf for flat countries. And it's the only one we know, Kipsy. So this is a country and it's flat. And each boundary, touches a different country. Do I have a preferred yarn? Well, yes. I use this one's, this is Simply Soft Caron because it's cheap and it has an enormous amount of colors. It's nice. But then I decided that I deserve better. This one is some yarn I love. It's called Malabrigo, and it's more expensive, and the colors are incredibly beautiful. It's a little thinner, but they both work. This is not, so Brandy says, this is not a virtual background. This is a real background. As virtual as me. I mean, we're all a little virtual here. Oh, I don't know, Cascade 2020, I don't know. Yeah. Oh, So Josh, do you crochet? Oh, we should talk. The best back. Oh, okay. Yeah, I really like when people like my thing. It's like it's they're part of my joy. As I said, I take any chance of joy that I can have. I can show you one more thing if you want, or I don't want to take all the time.
Well, let me just announce, I just heard from Kumar. He's not able to get into the conference quickly enough to give his talk. So we'll be canceling Kumar's talk. And let me just double check. We will be resuming, oh boy, we will be resuming with Thomas Forgach at 2:30, which is, who knows what time that is in your time. I guess that's 4:30 Eastern time, 1:30 Pacific time. So we'll regroup in about 30 minutes. So we can just use this as a forum to discuss whatever we want to discuss. So if you want to keep talking, Moira, that's fantastic.
Yeah, but I would like, people should ask. I mean, it's all, this thing that they can't talk.
Yeah. So people can request to share your screen, I believe, or not share your screen, but request to use your video, up to 20 people.
No, it's just, yes. I mean, I miss giving talks in person, so it's just interacting with people and showing and listen.
Yeah, so if anyone wants to request to have their video show so that we can interact. Yeah, so I'm going to let Josh in here. You can let some folks in. Oh, did that work? Josh, I thought I just, oh, here we go.
Hello.
Yeah, anyone who wants to join, you can come join for the next 30 minutes. We'll have a social half hour.
Well, since we went in the direction of mathematical crochet, I wanted to show that.
Oh my God,
off.
that's lovely. Yeah.
Heather Lewis and I were just talking about it out of band, if she's still here. I don't know if she has anything handy. Most of my other stuff is at home and I'm in my office. But yeah, crochet is really nice for illustrating mathematical surfaces.
Yes.
So have you done the thing where you, Maura, where you stitch a curve onto the surface?
Yes. But it's okay. I liked it, but it's, I don't know, it seemed, yeah, I don't know. It didn't seem totally, I don't know, organic.
Right. So how did you do this? The soccer ball that's behind you.
The soccer, this?
Yeah.
Oh gosh, these are from this. Well, there's this fantastic mathematician called Alicia Bull-Stott, and I'm Alicia Bull like George Bull. She's the daughter of George Bull. She's a fantastic, incredible person, and she studied the regular. So you know the Platonic solids. I have here some of the Platonic solids, the cube, etc., etc. Well, you can study the same thing, the analogous thing in dimension 4. And she was born in 1860, but she started to learn a little bit about 4 dimension, and then she studied sections of, she discovered, she's another amateur mathematician, really, like an undergraduate with no education, but no formal education, lots of education. So intersect these 4-dimensional things with a plane. And the idea, well, these ones are sections of this 120 cell. So this is a piece of the 120 cell.
Sure.
Which is made of dodecahedron. So you can think you have one dodecahedron, this is my fist, and then it has 12 faces, and I'm going to glue one dodecahedron in each of the faces. And I paint the first layer, say yellow, the second layer, red. And then I'm going to paint another layer, that's how I can think. And then when I intersect it with a plane, each layer will be colored in a different way. So she made models in cardboard, which are fantastic. And I'm writing a book about her. I'm totally obsessed. Anyway, and you can Google her. You can see some of her models. So these are some of the models she made. She drew and she constructed in cardboard. And they are, so see, it's really, this is a buckyball too, but, yeah. Yeah.
So are those crocheted? Are those granny squares, or was that
Yeah,
something else?
this is all crochet. I don't know if you can see. Yeah, this is crochet.
Yeah.
But you're going to see the floss if I put it too close. So.
And then you have the cubes in the background too, it looks like.
The cubes, yeah. Because, you know, when you want to make, so this is something I adore, you know, like, so this, imagine that you're two-dimensional and you want to understand the cube. So, well, this is one way, you know, you cannot move from this plane, but you can indicate, you know, which side is glued with glue, and then this is a way of understanding the cube. With one more dimension, I can fold and get a cube.
So I've been playing around with that also, but embedding them in into blankets by color.
Nice.
And then it turns out that all of the nets of the cube you can do by they can all be embedded, and then you can fold them up using 45-degree angles. So I've been
I don't understand that. What do you mean?
That you can so I've been playing with magnets, but if you can put magnets on the embeddings and then fold them up and form cubes.
Oh.
So I wasn't sure at first if that would work if they're embedded in the solid space, but it does. Though it gets
This is for all, you said for all the nets?
For all the nets of the cube. Yeah. It was a lot of little paper. I had a lot of little paper models at first.
Wow. Well, and then what I did is, this is the net of the 4-dimensional cube.
Nice. Yeah.
Which since I crochet in the round, you know, it's a little twisted occasionally. But, and I also made, so these cubes are all the cubes that make the 4-dimensional cube. You know, you can glue them, you know, that's all indicated. So here I have, for instance, two sides, here, that I'm going to glue. And, you know, and then here I have another one like this. And anyway, so there are 8. Just drop one. And I did also the same thing with, this is the simplest in dimension 4. It's made of 5 triangles. And I made the triangles, not tetrahedra. And these are the tetrahedra that, you know, again, same principle as before. And this is my last, you know, this is because I'm following Alicia Bull's steps. So this is, again, like the net of a, you know, 4-dimensional cube, you know, it's not, you know, but each cube is colored differently. There's an inside cube there is colored gray, you have to imagine. And now we're going to intersect this cube. We are going to fold it and make it in 4D and intersect it with a 3D plane. And I think, let me just see which is there. So yellow, blue. What's this? I'm going to start here. So here I have a tetrahedron. And this is, I'm going to start at this point, this point here. And imagine that I want to intersect this with a plane. Again, this point is a point in the 4-dimensional cube. So if I were intersecting only this little cube here, the green cube, I will get a triangle, you know, and if I move in the right angle, it would be an equilateral triangle. So you have triangle here, triangle here, triangle here, and I also triangle in the inside cube. And when the triangle, I know I'm going a little too fast, but you know, when the triangle gets biggest, the largest, it will have this side, and this is this tetrahedron. So this is a section of the cube when I start at a vertex and I move far away, far away, far away. And then when I move a little more far away, further away, these points here become triangles. And the triangles become hexagons. And Alicia Wool could see all this in her mind. I mean, my mind is blowing thinking about her mind. And then you get, this is I had to make it again. This is an octahedron. And then so what you get is this sequence, you know. tetrahedron, then this weird shape, then the octahedron, and then they start again. Another of this shape, and then, like these are the combinatorial shapes that you get.
I love that. I love the fact that they're tactile.
Yes,
And
yes.
so you can pick them up and move them and to help see.
Totally.
The fourth dimension is hard
no,
to visualize.
But nothing is, once, I was the same, but once you start really going there and, everything is until you think for a while on it, it's like, it's just, fourth dimension has maybe more halo, but they're all the same.
Moira, you mentioned working with a high school student,
Yes.
and it made me think about what is kind of the minimum requirements for students that you work with? Like, what kind of mathematical knowledge do you want them to have?
No requirement. I want energy to work. The thing is, my goal is not to produce a publishable paper. I work in a different philosophy. I really want people to learn something about math. And this is usually when I work is often, this girl was special. This one from this program, the Primes program from MIT. So this is super fancy and they are super selected. She was like a gift of, the mathematical goddess to me because she was absolutely wonderful and, really nice and incredibly smart and incredibly hardworking. So, but because if they don't want to solve something, I just meet them at the level they are. And I find something for them to understand or learn. And I have a student who, had some people are connected, and he just studied combinatorial things. I just want to see some progress. Some of them do papers, but that's not the goal for me.
Do they all write something, even if the goal isn't to publish papers?
In the beginning, I didn't do that, and I learned that it's much better. Yes.
Mm-hmm. So for people who aren't familiar with writing proofs, how do you help them to learn how to write, like in a mathematical way?
What I try first usually is people who likes math, and they're because many people, when you say proofs, they get goosebumps, not the good kind. But I just, because the point is understand. When they understand, they can write something. It's very, maybe you're imagining, something very, elevated it could be like a little summary. It doesn't have to be, like a fancy or, they can write why is true, whatever it is. And it's a little argument, not a formal proof.
Gotcha. I think we have a lot of expertise in this room. If anyone else wants to jump on, I think there are a lot of ideas in this room about how to help students write, how to help students get their hands dirty with new problems without a lot of background, that maybe would be fun to share some stories and ideas. If anyone wants to request to join us, you can make a request to share your video and audio, and I'm happy to invite you in. But I think this is a cool conversation, and I love, Moira, that you can meet students wherever they're at. I think that's pretty awesome and rare.
Well, yeah, at some point it was fantastic. We did this work in the summer where we had we got together, and there were high school students and grad students and professors. It was like, and we discussed math, and it's about ideas, and I think there's things that we can all learn in that way.
There are a lot of areas of math where you can just start by, drawing things or doing a few simple computations. And I'm a number theorist, so there are still a lot of, open, accessible problems where you just, say, start computing this, these numbers and see what you see.
Well, I'm thinking also of what Colin said about, so then you take this idea and you apply it to this other situation and just what happens, the kind of exploration. And that seems like a nice entrance in as well.
Yeah.
Great. Anthony, you joined us. Do you have some advice, words of advice for how to help students kind of get acclimated to research or how to write?
No, but I think you do. So, hey, I think a couple of years ago, you once I emailed and gave me this sandbox advice, which I really appreciated. Maybe you can say a few words about that. How like you're building a sandbox, and
Yeah.
over like multiple years, you can have students kind of exploring that area.
I like to invent new ideas so that every single question in that area is an open question. Like if you invent something new, then you kind of don't have to worry about people scooping you or anything like that. And there's a lot of low-hanging fruit. So most of my research with students is on games that you can play on knot diagrams. And people can get a lot of intuition immediately. I mean, even high school, middle school students can get intuition about these games on knots. And if you invent a new game, then every question you can ask about that game is an open question. And what's really cool is if the students can invent a new game. I'm actually working this summer with a group with two chemistry majors who were in my Calc 2 class this year, who I just really liked, and I thought it'd be fun to work with them. And one of them just asked a really awesome question that led to our entire summer research project on a new kind of knot game. So, but I am struggling with how to help these calculus students figure out how to write proofs with absolutely zero background in proofwriting. So that's why I asked that question.
But do they understand what they're doing?
They do, yeah. It's just a matter of knowing what things have to be justified and what things don't have to be justified.
Oh.
That kind of takes a while to feel out.
Yeah, no, that's...
Because they can have good intuition about something that's coming from a place of deep knowledge without them actually being able to articulate why they know that thing. And so it's hard to tease that out. Oh, and I'm hearing myself talk.
Yeah, like a goddess.
That might be me feeding back. I'll turn my speakers down. But I was going to say that. What was I going to say? Oh, I don't really have any shortcuts for that process that you described about getting to the level of describing enough. But I plan for doing a lot of iterations, and I tell them that writing math always takes a lot of iterations. Professionals writing papers are always revising and resubmitting and posting preprints and getting comments from people. And so, I tell them it's not a bad thing if, their first draft is 1 page and I'm like, okay, here are 16 places where you have to explain more. That's okay.
You're making me think I want to share a piece of completely unsolicited advice. I got a CURM grant to have a research group last year. And the way CURM, so this is Center for Undergraduate Research in Mathematics, the way it works now is you apply in pairs. So there are 2 faculty members at institutions that are maybe geographically in the same place, who are going to work together with 2 groups of students at their home institutions on research. So I was working with Jen Townsend, who is a professor at Bellevue College, which is close to Seattle. And she said, I'm going to have weekly meetings with my students one-on-one in addition to having group meetings, so I can hear from each student individually about how things are going for them. And so I thought, oh, I'll do that too. And it has been totally transformative. When I'm working with a group of students, I've never before done this before I did my CRM year last year, but meeting one-on-one with each student every week really helped me figure out like when students are feeling like their contributions aren't good enough. So I had a student share with me after I just ripped apart her writing last week, that she just kept on apologizing for how bad her writing was in our one-on-one meeting. And it gave me an opportunity to put in context that it's part of the process to have to do a significant amount of revision, and to remind her that she's not an expert in this area and it's a learning process. And just having that opportunity to hear how students are thinking about their contributions and to give them pep talks or just to give them encouragement, let them know that the work they're doing is really awesome, because they don't realize, when you think your students are doing a great job, they might not know that you think they're doing a great job. So it was just a great place to get to talk with students about their concerns. And then if there are any issues with group dynamics, with people not getting along with each other very well, it's a great opportunity to kind of hear about that early on and nip problems in the bud. So that's my one piece of unsolicited advice to anyone mentoring groups of student researchers. Consider having one-on-one meetings. And these can be 10 or 15 minutes a week. It doesn't have to be a big time commitment, but it's really helpful.
That's actually good to hear. Sorry, go ahead, Anthony.
Yeah, I was just going to say that's fantastic advice. I was going to ask if you had suggestions for how we communicate our students' work to the rest of campus. For instance, we have like poster sessions and undergraduate research sometimes. And, sometimes I have my students, I like knot theory. So I'll mention like, talk about DNA or something. But then everyone's asking about DNA and their work is not about, anything to do with. And so it becomes this weird thing where it's like, should we mention applications that don't relate to our work or not? Should we frame it as just a game? And then that seems like maybe it trivializes the work. Do you have any thoughts on how we can frame the work to a broader disciplinary audience?
Moira, what do you think about this? Do you have your students talking about applications?
Well, that's a question that comes out, with certain frequency. First, I said, I'm honest, I really like mathematics because I like it, and it's irregardless of the application. I see math everywhere, but if I didn't, I think I would like it anyway. It just fascinates me. And when a problem of math intrigues me, it's just, I don't know exactly what it is. So at first I say that. I said, I know there are many potential applications, but then I tell the story of all these areas of mathematics that were developed by their beauty. And then, it's like we are in a factory and we make tools. And then the people, the mechanics who are going to fix the planet come and grab the tools. And I said, you use number theory, the most, useless theory that thought when it was done, just for the beauty, and look how important it was, and DNA with all this topology, and, so. But I make the tool. I don't see how the tool is used.
For myself, when I'm giving a knot theory talk, I'll always try and mention applications. But I'm pretty clear about like, here's an application and I'm telling you the extent of my knowledge right now. I can point you towards some resources if you're interested in learning more. But my work really goes in this other direction. And so maybe if you tell them a few words like that to say, like, this is a cool thing, I can tell you who's working in this area so you can look up some resources. But I'm going to be talking about this other aspect of knots.
I find that it really pays off to learn, like one application that you can explain, and it doesn't have to be a practical one. So I'm like I said, my research with students is in number theory. I always relate it to cryptography. I try to have at least one crypto system
Josh, I can't hear you.
that really
I mean,
has
your
something to
sound.
do. I think it's the connection.
Oh, I see.
Yeah, I'm having trouble hearing everyone too. I'll try to speak clearer.
You sound like an alien.
Slower though.
By the way, I'm just
We all
gonna
do.
I'm gonna encourage Tom to hop on here. So because in just a minute we'll have Tom try and share his screen because we'll need to get ready for his talk. But
But
yeah.
I often need to have a disclaimer. You know, this is not a crypto system anybody would actually use in practice. It's too slow. It's not secure enough. Whatever, and nobody really cares, right? So, you know, if you can have some tangible relationship with an application, you know, even if it's really strained, it helps them latch onto it.
Great advice, Josh. Thank you to Josh and Heather for joining us. Moira, thank you for leading such a
with
cool.
the service I'm working on now.
That's awesome. You were actually the perfect person to have speak just before a cancellation in a talk. So thank you so much. If
Oh,
you
my pleasure. You know, I would love to. Oh, look at that.
So
okay.
Tom
Goodbye.
is going to be speaking with us in a few minutes. Yeah, Heather, thank you so much.
Bye-bye. Thank you for
Bye.
listening for so long.
Yes, thank you. It's really great to see so many people so enthusiastic about this stuff and sharing their enthusiasm with students, bringing students in to research in a non-threatening way. That's really amazing. All right, so maybe we'll just take a breather for a minute and then we'll invite Tom to speak with us. Looks like everything's working great for you, Tom. Does your cursor work? I mean, can we see your cursor? That's a good thing to try and test out. Oh, yep, I see your cursor. That's
going on
great.
here?
Yep, yep.
All right.
I don't know why we couldn't see it with Colin.
Well,
I'm sure that's
maybe
annoying.
the conference decided no cursoring allowed in public speaking.
Great. Well, thank you so much for coming to talk with us today.
My pleasure. Well, that's a good discussion. Actually, it almost perfectly sets up some of the stuff I put in the talk. So I think it will be a seamless transition from. We'll see how it goes.
That's awesome. Yeah, I would love to hear your advice on helping students who don't have a lot of writing background, helping them learn how to write and be okay with being severely critiqued.
I find that a lot of times it's not even about math. They cannot articulate what they're thinking, just plain English. They think they're saying what they want to say, but they're not. And that just takes practice.
So if someone says some sort of nonsense to you and you know that in their head they have kind of the right mathematical picture, how do you help them clarify the nonsense?
Well, I think those are great opportunities to just actually record the sentence, right, and parse, and then have them understand this is what you just said. That's
great.
And then let's see what you really wanted to say, and then take away the stuff and correct it. There's a method called the red line method for correcting homework. It's extremely time sensitive. And so you can do, they turn in the homework if it's just a short write-up problem, you just draw the red line at the first mistake, logical or otherwise, and give it back to them. Say, okay, what's wrong here? Can you fix it? And do that a couple of times, and then, you know, it's a little bit of back and forth. I feel like it elicits more participation from a student than if you just give them a correctly written up solution you did.
Mhm.
So very little connection to that. Might not even read it.
All right, well, we're at that time. Tom Forgach from Fresno State is going to talk to us. I'm not quite sure what you're going to talk to us about. So your talk title is Elementary, maybe for Watson. So it's an exciting mystery. Please take it away, Tom.
Thank you, Allison, for the invitation, and for all of you for sticking around. There's some wonderful segues to the discussion and the previous talks leading into this one. Mostly in some of the ways that what I'm about to talk to you about and describe are different from the experiences in the so maybe the approaches from the first two talks that we heard today. And so my interest, we run a number of REUs at Fresno State, and we're rather familiar with the summer-long setups for undergraduate research with concentrated efforts. Then we also had within the department exposure to Kerm, as Allison was talking about, maybe some of the early iterations of it, and PUMP. Those are also extended research opportunities for undergraduate students that are externally funded. And so every time we reapply for a grant, you get this thing, well, okay, but when are you going to make this, you know, part of an institutional effort? And so the obvious thing to try to do is to somehow try to grow these things organically out of the classroom. And there's some effort in that coming out of Georgia, and Dolan is a leader of this, called CURES, and course-based undergraduate research experiences. And I implore you to just try to sit down and create a really good, engaging version of this, if for no other reason, to sort of get a good feeling of how difficult that is. And so that is what these projects I'm going to talk about sort of came from. That was the approach. I was trying to get a class to do beginnings of undergraduate research. And so the elementary part of the title refers to actually the class and the material. So I was teaching elementary number theory. There's an introductory course, sophomores, juniors, early juniors take it. And other than, in addition to the name containing the word elementary, and for the course, it's designed to be a course that you can take immediately after you've taken our introduction to proofs class. But the mathematical concepts built from the ground up, they assume no real prior knowledge. And so in that nature, it's perfect for students to get involved and get going, and see how some of the notions are developed. So that's part of what goes into elementary. Because of the concepts being simple in elementary, there is essentially no barriers to entry. As you take students along on some of these projects, they are inevitably faced with having to build on the concepts they learned in class, and so that introduces them to this other aspect of research. Is, okay, I know something, I know A, B, and C, but I'm going to need to also learn D and F in order to be able to make progress on this particular problem I'm looking at. But it grounds the effort in a course. And so it's sort of a double-edged sword. It cuts both ways. It motivates them to do well in the class, right? Because they need to learn all that stuff to do well in the research. And also they see why the class is important. Sometimes, especially in these introductory courses, I'm sure we've all heard, so why do I need to learn this? Why is this important? Especially from students that are not necessarily math majors, right? Now, this course is by far and large populated by math majors, so maybe we'll hear that a little bit less, but nonetheless, it's always good when a student can organically understand, okay, well, I learned some rudimentary material, I'm using it right away in some project that's not part of the course and takes me in fields I've never seen before, and I'm asked to learn about myself. And then a third aspect of the group under the elementary part of the title is oftentimes the results, and existing and new results, are oftentimes really easy to state. They're just elegant in their simplicity. Although the proofs that go in establishing them can be quite complicated. Still, oftentimes they don't require any advanced proof techniques beyond, combinatorial counting techniques and such. And so in that regard, I think are quite accessible to the students. Now, Watson enters the title. And unashamedly, I stole, of course, the name from IBM's computer. And it is a reference to computers, how they can be used in projects that I'm going to be talking to you about. And so that's the title. And of course, putting it together, there you have it, elementary or not. Now, I would like to say that these projects are in elementary number theory, which is not my main research area. I'm an analyst. I'm a complex analyst, maybe a little bit of analytic number theory. Nonetheless, I think this is the best course that we have on in our catalog that allows for students to enter an undergraduate research project. And so I basically said, all right, let's do it. Which, of course, I had some experience in research, but hardly any in number theory research. And that helps, I think, cultivate an environment with the students where you're a team, right? You're discovering things at the same time. And it's a little less of more of an equal base footing or equal footing than if we were to do something in complex analysis where, for various reasons, I think there would be more of an imbalance from the student's point of view, even whether or not that's intended by me. Okay, all right, so origins. So this particular slide is hoping to address some of the questions of where do people find problems? How do you know that a problem is accessible to students? And as Colin said, a lot of that comes from experience, but a lot of that you can sort of farm out and look for resources where the writers in those resources had given thought to this issue and included problems that they thought would be accessible to students. And so the two problems I'm discussing came from two different sources. The first one on Betty sequences came from the monthly. And this was, students were in a junior seminar that cast explicitly is for find a project that they can do individual research on in the following semester. And so in this class, I assigned some readings. The notes and problems in the monthly are a wonderful resource for this. Notes are capped at 5 pages. They're not too long. And the problems are just short and exciting and cover various different areas of math. And so a student picked the problem first and said, do some reading on this, sure. So that's how Betty sequences came about. Of course, the monthly is monthly, so every month you'll get to see new and interesting expositions and discussions on various different topics. The other problem I'll talk to you about came from this absolutely wonderful book called How Round is the Cube? And this is a publication, an MSRF publication for the math circles. And so Maura also discussed this sort of vertical integration with high school students and graduate students and faculty working together. And math circles run at every level, essentially, of pre-college. And I can look at this, and I do look at this as, okay, these problems are really accessible. They should be just perfectly at the level where undergraduate students in an elementary number theory class, for example, could take up one of these problems and start digging and take it as far as they can. Now, this particular book contains, I think, 35 different essays, and not just on elementary number theory. There's projects in there for calculus students or calculus flavored. There's not theory projects in there. There's all kinds of stuff in there. It's a wonderful collection. But anyway, highly recommend it. if you're looking for projects. And they come with an introduction. So you can lecture on that introduction or just give it to the students to read for maybe a couple of weeks in the semester. And then they culminate, each of these essays culminate in a research corner. So they already pose a couple of questions that you can start with, and then you can take it from there, if you will. Okay, so Betty sequences. The Betty sequence is really a sequence of integers defined this way, an associated density that what we call alpha. It's a famous theorem, old theorem of Betty, that if you have alpha and beta both irrational that sum to 1, well, we like them to be positive, and then the associated Betty sequence is partitioned in natural numbers. And so Ouspensky, this is 1929, proved that a collection of Betty sequences will partition the natural numbers if and only if either there's only one of them or there are two of them and their associated density is satisfied this condition. Okay, so the proof, Ouspensky's paper is actually a wonderful paper to read, and it could serve as sort of a reading project for an undergraduate student. They'll learn a lot of analysis, actually, which is what caught my attention. But so partitioning with beta sequences of the natural numbers, you either have one or two. Okay, so here's a picture of an instance of a pair of beta sequences complementary beta sequences associated to the densities 1 over pi and 1 minus 1 over pi. Right? One of the few reasons I included this picture in the talk is they say every talk should have a picture, so here it is. The other one is that it illustrates or lets them talk a little bit about how students' contribution to the problem can start by simply computing or coding known facts or examples, as some of the previous speakers have mentioned, in Mathematica or Sage or whatever else, whatever other computer language they like to use in whatever area they're working in. And these computational examples and pictures will lead to conjectures that can later on be either proved or disproved. And so one can do this and lay out the sequences forever and ever and see how, whether or not there are patterns, right? If we only looked at, let's say, up to about 20, we may think that, oh, well, maybe there's 2 to 1, 2 to 1, 2 to 1. And then you realize at 21, it's a 22 through 24, that's 3 of one kind before the other kind shows up, right? So simple visual checks can dispel with some of the ideas that are obviously not true, but may lead to conjectures that are in fact correct. Okay, so if you have 3 partitioning sequences of the integers, cannot all be Betty, right? And so what's the next best scenario? And so Adolf Hildebrand, Lilly, and Xi, this was done at the Illinois Geometry Lab. Paper came out in 2019, discussed what they called almost Betty partitions. These are by sequences that are not Betty, but maybe almost Betty. So you may have 1 Betty sequence and 2 almost Betty sequences to partition the integers. And for them to develop this, right, it's a wonderful paper to read because the students, if you have your students read it, can go through, okay, well, what did we need to do? We need to understand what it means not to be a Betty sequence and what a perturbation of a Betty sequence is and how do you measure that, right? And so an almost Betty sequence, it's essentially a sequence of integers that differs from a Betty sequence by a bounded amount, right? So entry by entry, so it's a soup norm on the entries of the sequence. That thing is some finite number. Okay? So students can start learning about a lot of related mathematics that are not necessarily number theoretic, right? So there's an analysis involved there, and questions that come up. Oh, okay, is that the best way to measure closeness or not? Okay. And they give results on the partitioning with 3 sequences, but they also pose a number of questions, and these are open, right? So can we use what they call non-homogeneous Betty sequences of this type to partition? If so, how is that going to be done? Can we partition with more than 3, right? 4, 5, or n almost Betty sequences? And what are the related results related to those types of partition. Okay, now those last three bullet points here actually appear at the end of that paper by Hildebrand et al. I had some students approach this question from a different angle, and actually that was before the Hildebrand's paper came out. So it was lovely to see that this actually is a problem that's interesting to more than just me and some of my students were. But what we were looking at is, instead of looking at the number of Betty sequences and understand means not necessarily to be Betty, we try to generalize the notion of the density. So instead of thinking about the density of as a constant, right, you could think about that as a function, and then ask yourself, okay, what properties of this function would even make sense, so that the questions still are sensible to ask. And once you answer that, then go and try to find out what kind of partitioning results you can get. Some of the obvious things, the first things that you might try is to say, okay, well, what if you restrict your attention to monotonic functions? And what if we allow shifting of these functions, so you can only look at maybe a tail, and a tail of a monotonic bounded function, right? If that's about as close as you can get to a constant function, and that will let you relate some of the partitioning results. Interestingly enough, if you look at monotonic functions far enough out, one can prove that any initial segment of the natural numbers can be partitioned by a Betty sequence associated to such a density function and its complement, but they all fail. None of them will actually partition the entire set of integers. So there's some lovely mathematics going on there, but the questions are still open. Okay, so I'm going to switch gears and talk a little bit about the second set of, well, you're right, yeah. So notions developed by Hildebrand, are they or are they not adaptable to a generalized notion of density in that setting? So the second sort of problem I want to talk a little bit about, also elementary number theory, and is related to very triangular numbers. The original problem is posed by James Tanton in the book I showed you a little bit. So a triangular number, we all know what triangular numbers are. A very triangular number is a triangular number whose binary representation contains a triangular number of ones, because it's a mouthful, right? But so you take a triangular number, you look at its binary representation, and you count the number of ones. If that count is also a triangular number, you have yourself a very triangular number. And so Tanton, in that essay, includes a number of PISA results. First of which, that there are infinitely many of these. But it's a lovely introduction to a student to have them read that and see if they can also prove that there are infinitely many of these numbers in a way different from how that was presented by Tanton. And I think that's generally an excellent way of engaging undergraduate students, in understanding what they have read, because many times if they do understand that, they can oftentimes in these simpler cases find an analogous but different way, or maybe a parallel but different way to prove the same result. And those are fantastic. And with Ellison, I think refer to these as somewhat low-hanging fruit, but that's okay. You pick one we pick one we can get. Okay, so there are infinitely many of these. In addition to that, and I proved this with a student that I worked with during the academic year as an independent study, it's essentially the twin triangular number theorem, although we proved a different version that I call the sextuplet triangular number theorem, which says that there are infinitely many strings of 6 consecutive triangular numbers that are also very triangular. And so, lovely result. And we also proved Bertrand's postulate for very triangular numbers. And so if you find the nth triangular number before you hit the 2nth triangular number, you will find a very triangular number. Okay. Then we also proved that there are arbitrarily long gaps between consecutive very triangular numbers. Of course, the investigation here, you don't run your investigation in this particular setup in the integers, right? You take a step down and you consider only the triangular numbers, and you wonder where the very triangular numbers are amongst all the triangular numbers. Okay, so when I'm talking about gaps, right, those are gaps between very triangular numbers in the mother set of triangular numbers, but they're arbitrarily long ones of those. And so if you look at these four results, there are corresponding theorems just exactly like these for the primes. And I find it just extremely satisfying, because in our elementary number theory class, they will see the fact that there are infinitely many primes. They might also see that there are arbitrarily long gaps between consecutive primes within the integers, right? Those are pretty simple results that make it through almost every elementary number theory class. The twin prime number theorem, well, probably not. That's a tough one. But Bertrand's postulate might. Okay, and so I feel that the students having been exposed to these, or having seen them in the class, and then being able to prove something analogous in their research setting is rather satisfying. The last one I want to mention here is that the density of the very triangular numbers in the triangular numbers, well, the upper density is 0. And this takes some sophisticated understanding of well, analytic number theory, or you can just take the result from analytic number theory and apply it to this particular setting. The proof that we gave here, and I must give extensive credit to the editors of the journal where this paper is currently being reviewed, for helping us put together the proof of this particular result, is absolutely wonderful. It uses basically quadratic residues, which we cover in our elementary number theory course towards maybe the 3/4 mark of the semester, so maybe week 12. But the students do see it. And so here's an application of all the things that they learned about quadratic residues. And this particular student had discovered that they needed this result in order to be able to prove something related to the upper density of the very triangular numbers. The reason why this result is important is because it's kind of shot our hope of using positive upper density as guaranteeing arithmetic progressions existing. So many arbitrarily long arithmetic progressions existing within the triangular numbers. Okay, so of course, what we would like to know is whether or not it is true that there are many arbitrarily long arithmetic progressions in the set of very triangular numbers. Also open is the question whether or not, given any integer, you can find k consecutive triangular numbers that are all very triangular. So we've been able to show this for k equals 6, and of course, henceforth k equals 1 through 6. But I actually think that it's true for every k. And the reason I think it's true for every k is based on computer experimentation. I should say that our computer sort of died when it hit computational complexity of the order 2 to the 30. It's just not very good after that. But it also gives students an opportunity to try to improve on computational efficiency when they work on a project like this. So they might start with a number theory project, may end up with a computer science project if that's what they want to work on. Of course, the holy grail is there a formula for the very triangular number? If there is, we have not been able to find this. And so the very triangular numbers, right, are given by an explicit, the triangular numbers, sorry, are given by an explicit formula, n times n plus 1 over 2. But there are other interesting sets of numbers, right? So you can do square numbers, trapezoidal numbers, hexagonal numbers, ask the same question. Binary expansion should contain a square number of ones, trapezoidal number of ones, hexagonal number of ones, etc., etc. See what you can prove about those. and whether or not the results known for the very triangular numbers carry over, and how much does this depend on the degree in n of the formula you have. So triangular numbers are quadratic in n. If you look at that closed form expression, maybe there are other interesting sets of numbers where that polynomial degree is large, or as large as you can make it be, and maybe things are still okay. You can also from binary representation to base 3 representation or base q representation. Sky's the limit there. So I just want to finish here by pointing out that students can take the following directions here when studying these questions. They can learn about analytic number theory, combinatorial number theory, computational efficiency, as I alluded to, classical real analysis, and of course, elementary number theory. And so here's a list of papers that if you were so inclined to maybe start a research project with a student in this area, I think this would set you up very well. But if it's too many, by far and large, I would start with Tenton's collection of essays, because they're just a wonderful starting point. Thank you for your time. Sorry for running over.
Thank you, Tom. Yeah, great talk. Thanks so much, especially for the kind of general advice at the beginning. Great open questions. Since we only have 4 minutes before our next talk with Laura Pudwell, I'll suggest that people type questions in the Q&A, and Tom, if you can write answers to the questions, that would be great. Otherwise, thank you so much. Let's give Tom our appreciation. And in just a few minutes, we will have Laura Pudwell giving a talk about patterns in trees.
And sure, I just click on the button that says leave here, right?
I think
so. Is that correct?
I think so. I'm
always. I'll stop sharing.
Okay. I think that'll work, Tom.
So I stop sharing.
Okay.
I'll leave.
And just thanks again for participating and giving a great talk in our session. We really appreciate it. Hi, Laura.
Hi, Allison.
Before your talk, I would love to give a shout out or a little plug for our business meeting. The Sigma on Undergraduate Research is having a business meeting on Saturday at 10 a.m. Mountain Time. And the meeting will be kicked off with a featured speaker. Pamela Harris from Williams College will be giving an invited talk called Using Restorative Practices to Build Research Communities. And that talk will be followed by our business meeting. And we are going to be having elections for a few of the positions on the leadership team, including my position, which basically is event planning for the Sigma. So if that's something you're interested in, I encourage you to attend the business meeting and learn more about that. Also, something Tom was talking about reminded me of the FIRM series. FIRM is Foundations for Undergraduate Research in Math. It's a Springer series of books that's published by Aaron Wooten and edited by Aaron Wooten and a number of other folks. These books in this series basically discuss different areas that are accessible for undergraduate research and give suggestions for problems that students could work on. And there's a new 2 volumes for this series that are going to be coming out in the next year or 2 that are focused on problems that are accessible to students with very little math background. So keep an eye out for that. Thank you, Brandy. I knew you would help me follow up on that. So lots of great resources out there. And Laura, are you feeling like you've got this technology under control? Can you use your pointer?
Oh, yeah.
Awesome.
I gave a talk yesterday too, so I'm happy with the setup.
Fantastic. Well, according to Colin, the technology might not behave the same way in 2 different talks. So I'm glad it's working here. All right. So I am super happy to be hearing from Laura. We've organized this session before, and Laura has given talks for us, and we've been super excited to invite her back because her talks are always very interesting and accessible. And even if you're not a graph theorist or a combinatorics person, you might feel like you could get started on the problem she's going to be talking about, which is just where we want to be when we're, introducing students to open problems. So Laura, without further ado, please take it away. Tell us about patterns in trees.
All right. Thank you for the introduction, Allison, and thank you for putting together such an inspirational afternoon. So I've been enjoying the variety of mathematics going on today. And I'm also really excited to share this story because it's one of my favorite stories of one research project leading to another and another and another. And as Allison said, my hope is that even if your area of interest is not combinatorics, what you take from this is kind of an example of how one research project is led into another in at least one other context. So first, why patterns in trees, or even what are patterns in trees? So of course, I don't mean the nice green trees outside that give you shade on a hot summer day. I mean graph theory kinds of trees, like the one you're looking at here. One reason some people care about trees is because they're a great model for how you might store information in an organized way in a computer. So for example, the tree that I've put on this intro slide comes from taking a derivative of the delightful function you see over here on the left, where of course you need a chain rule and a product rule and another chain rule. It's a mess to write out by hand, but if you ask the computer can do it. And here's a tree representation of the result. You have cosine of the stuff that's inside the outermost parentheses times the derivative of that. And what I want to point out on this tree is there's a lot of repetition. This wasn't a convoluted tree I made up just to make it be a repetitive tree. This is a tree that showed up as a result of a mathematical computation. And you see, for example, e to the power x plus 1, 2, 3, 4, 5 times across the bottom of the tree. If I cared about how to store this tree more efficiently in computer memory, and I saw something with a lot of symbols that showed up repeatedly, I might just use one symbol for that expression, and then I have a lot less to write the many, many times it shows up. So that's one motivation for looking for smaller trees that are inside of larger trees. Now, in the rest of the talk, I won't be thinking about computer memory so much, but this idea of smaller trees inside of larger trees, that's the motivation for caring about tree patterns. Let me tell you more about the particular trees in this talk. So there's lots of kinds of trees out there you could think about, but I'm going to think about trees that are rooted, ordered, and full binary. So rooted means that there's a special vertex at the top of the page, and then the children are below it. So the root at the top of the page is more of a family tree kind of word than a ecology tree kind of word. But that basically means I can tell the difference between up and down when I draw these trees. When I say they're ordered, that means I can tell left and right apart. So the left child of a vertex is different from the right child. There are some contexts where people might say the two trees here are the same, but because I'm talking about ordered trees, these are actually different. You can see that there are 5 vertices to the left of the root on this first tree, and there's 7 vertices to the left of the root on the second tree, and so those are definitely not the same. And finally, I'm going to focus on full binary trees. That means every vertex either has exactly 2 children below it, or it has 0 children below it. And the vertices with exactly 0 children, those are called leaves. So I guess mixed metaphors there, but following convention. And so throughout this talk, the rooted, ordered, full binary trees with n leaves are going to be referred to as T sub n. And the question I'm interested in throughout this talk is how many trees in T sub n avoid a given tree pattern. Now, I didn't come up with this on my own. I was actually inspired by a talk at the joint math meetings about a decade ago. So my next few slides are going to show you the definitions and results from that talk that inspired me. So the definition of one tree being inside of another from that talk is that big T contains little t if you can find little t as a contiguous rooted ordered subtree, which is still a mouthful. But contiguous basically means all close together and adjacent. So here's a tree with 5 leaves on the left, and then I've got 3 examples of 4-leaf trees over here on the right. For example, this one is contained inside the big tree because if you take the root here and lay it on top of the root here, you see exactly this 4-leaf tree at the top of the big tree down to about here. Similarly, this tree is inside because if you take its root and associate it with this vertex here and ignore everything above my cursor, you see exactly that tree. On the other hand, this last tree is not inside the 5-leaf tree because you can notice that the root here has a left child and a left grandchild and a left great grandchild. And there's no vertex in this tree that has 3 generations going left. And so when we say contiguous tree pattern, we really mean you can take the smaller tree, cut it out of the page, and overlay it exactly on part of the larger tree. So what happens when you try to count trees avoiding a specific pattern with this definition of tree pattern? Well, we'll start small and build up. So here's the smallest tree I can draw because we said all our trees have a root. What does it look like to avoid that? Well, all our trees have a root, and so the root is this. You might go, okay, that's a boundary case. Let's level up a little. So what does a tree look like if it avoids this 2-leaf pattern? Well, your root either has 0 children, in which case it looks like this, or it has 2 children. So the only thing that avoids this is the 1-leaf tree. Everything else contains this. Okay, so we've taken care of 1-leaf patterns, 2-leaf patterns. If I want to avoid this 3-leaf pattern, vertices can have children, but they can't have grandchildren to the left. And so anytime you go down a new generation, you're only allowed to attach another pair of children on the far right. And so there's only one way to build bigger and bigger trees avoiding this. It's where all your generations lean to the right. And finally, I'll do just one more example. Here's a 4-leaf tree, and you get to have a little bit more fun here. This tree, if you have it as a pattern, you have a vertex that has both left and right grandchildren. And so if you want to avoid this tree, at every generation, you can have grandchildren on the left or on the right, but not both. And that's where we're getting this power of 2 phenomenon. And so here's the collection of results you get from just kind of working out the cases and the structure for avoiding contiguous tree patterns with up to 4 leaves. We worked out the first few rows of here exactly on the previous slides. It turns out if you avoid this tree, there's a different argument for why you get powers of 2. And if you try to avoid this tree, you get what is known as the Motzkin numbers, which show up a bit in combinatorics and are a good sign that this problem is friends with other combinatorics problems. And what I just showed you is kind of an abbreviated version of an awesome talk I saw my friend Eric Rowland give at the joint math meetings about a decade ago on contiguous pattern avoidance in binary trees. And about 6 months later, I was going to have my first undergraduate research in a funded REU team. And I was settling on what problem to advertise as we sent out our REU materials. And I said to Eric, I loved that talk. Have you thought about this follow-up question and that one and that one? And he goes, honestly, those are all great questions, but I'm kind of done working with it. If you want to take it and run with it, please do. And so I shared basically what you saw at the beginning of this talk with this team of students here of Nathan Gabriel, Sam Tay, and Katie Pesky, and said, here are a few different directions I think we could go. What interests you? And they voted that they wanted to change the word binary to ternary and see what happens. And we had a wonderfully productive summer from changing one word in Eric's kind of thesis statement of what to look at. And so a little bit more detail about what happened. In Eric Rowland's work, he basically had an algorithm where you could input the tree you wanted to avoid, and then he could determine how many trees of whatever size you want avoid that pattern. One common move in enumeration problems is if you don't have a direct formula or a recurrence, or sometimes even if you do, the next level up is to take your sequence of numbers you're interested in and make them be the coefficients in a power series, and then try to understand the function that has that power series. That's what his algorithm was good for. This object is called a generating function. And he could prove his generating functions were always algebraic. And so this team of students was able to modify that algorithm for working with binary trees to ternary trees. But what was even better was the results they were getting out were hitting on a lot of other famous sequences. So it wasn't just, here we modified this algorithm, it was, and when the algorithm has cool outputs, can we find bijective explanations? And so that was honestly my first research project with outside of my own university undergraduate students. It came from taking a friend's awesome talk, changing one word, and seeing what happened. So then where do you go next? Because I'm not just going to go to 4-child trees and 5-child trees and so on. Eventually you hit a point of diminishing returns. What I did was looked for a different word to change in the problem statement. And so contiguous tree patterns is one way a tree could be inside of a larger tree. But why should the smaller tree have to be all together in one piece? And that's the idea behind non-contiguous tree patterns. In a non-contiguous tree pattern, you still want to find the smaller tree somehow inside the larger tree. But here we're going to let it be a little more spread out. So these are the same trees you saw on my previous example slide. But now, instead of having to be there contiguously, you're allowed to contract pairs of edges that had the same parent to get a tree that looks like your pattern. So these two contiguous patterns are still there. If I want to find this tree, I look at the top and I contract these two bottom edges into a point, and I've got the first pattern. If I want to find this one, it's still in the same place. I would contract those two edges that are above my cursor into this point here, and you've got the second pattern. But contiguously, we avoided this last pattern, and now it's there. If you contract the two non-bolded edges, this lower part of the tree really is left of the root, so it's not too wild to say this is one sense that this smaller tree is contained in this larger tree. So what happens when you let your tree patterns be a little more spread out? Totally different things than contiguous patterns, but very cool things. So I won't go through them one at a time, but you might think what's different from the contiguous tree pattern table. The first few lines are the same. Avoiding either of these two trees gave us powers of 2 before, but avoiding this last one gave us the Motzkin numbers in the previous table, and now it also gives us powers of 2. Is that a fluke, or does it scale up? Well, that's what the next team of undergrads I worked with was looking at, and what they discovered was they found a way to modify the algorithm that finds generating functions for counting pattern avoiding trees to adapt to this new kind of pattern. And they could prove any 2 trees with K leaves are going to get the same number of trees avoiding them. So think of your wildest favorite 37 leaf tree, and then think of a totally different looking 37 leaf tree. The number of trees on N leaves avoiding either one of those is going to be the same. And so then the follow-up question is, well, it doesn't matter what the tree looks like, just matters how many leaves. What do these functions actually look like? And since they were modifying algorithms, they could actually compute these generating functions for specific sizes of trees they wanted to avoid. Here are the functions they were getting that, remember, if you expand these functions in series form, the coefficients are number of trees with 1, 2, 3 leaves avoiding your pattern. This last column is if you're into counting things, the Online Encyclopedia of Integer Sequences is an awesome database of integer sequences. And so the coefficients we were getting were these particular entries in the OEIS. And now when I look at this list of functions, I notice things like, okay, these are all rational functions. I notice that the coefficients in the numerator and the denominator seem to be alternating between plus and minus signs. I notice that the denominator on each function, if you multiply it by x, you get the numerator on the next. But what I don't know is easy to spot at first is where exactly are these coefficients coming from? The 1, the 5, the 6, the 10, and so on. And undergrads have great eyes for these kinds of things. So I'm going to have the functions on the next slide again. What they noticed is this looks kind of triangular, and they had a favorite triangle, and they put them side by side. And now maybe you're spotting the coefficients too. They conjectured that these coefficients were really coming from diagonals of Pascal's triangle. So for example, this 1, 5, 6, and 1 come from this orange diagonal of 1, 5, 6, and 1. Well, once you've made that conjecture, then you write an induction proof that it's not just, hey, there's a nice generating function, but we can predict its alternating binomial coefficients that make up the numerator and the denominator. So non-contiguous pattern avoidance in trees, totally taken care of with an awesome, insightful team of students. And here's their photos. So that was the work of Sam Tyner, Mike Derrico, and Casey Wynn back about a decade ago. So far you've seen 2 projects I came up with by just having students look at a previous problem and invite them to change one word. We changed binary to ternary and got some cool sequences. We changed our definition of pattern and we got a completely different flavor of result. And so then when I had yet another team who was interested in trees and I suggested, okay, here's what's been done. What words would you like to change now? They said, why are we always avoiding patterns? What if we try containing them? Well, that involves going back and looking at the literature to say, okay, what's already known about tree containment? Because this was all inspired by a tree avoidance talk. And it turns out the results for tree containment have roots that are even further ago in the past. So almost 40 years ago now, the result for contiguous containment in trees is if you think of a K-leaf tree pattern, the number of times it's contained in the set of all N-leaf trees is given by this binomial coefficient here. So I'll make this a little more concrete with a picture on the next slide. But for example, if I think of a 4-leaf tree pattern contained in the set of all 5-leaf trees, this computation says that 4-leaf tree should show up 6 times total across all 5-leaf trees. And here are 2 different 4-leaf trees. And if you think about them contiguously and kind of take a census, here are all the 14 5-leaf trees. This pattern is contained twice in this tree, and once in this tree, and once in this tree, and so on. Notice it's contained 6 times total across all the trees. This one has a totally different distribution. There's no tree where it appears in twice, but it still appears 6 times total in the set of all trees. So that was the known contiguous pattern result. What happens when you switch to non-contiguous? Well, you experiment and look for patterns, and we were noticing the same phenomenon, that what seemed to matter was just the number of leaves, that no matter what 2 K-leaf trees you had, you seemed to get the same total. And so a result of another summers of work was that we actually found a 2-variable generating function where the coefficient of x to the n, y to the k ends up being the number of times a K-leaf tree is contained in the set of all N-leaf trees. That 10 is bold because it matches that 4-leaf tree number of copies inside of all 5-leaf trees. And so totally different flavor of result, again, from changing the word avoid to contain. And so as advertised at the beginning, what I'm hoping I convey here, whether you're interested in trees or something else, is you can get a lot of good research problems by just changing one word at a time in something else that inspires you. I heard a talk I really enjoyed, made sure I wasn't knocking the author out of the way on problems he plans to work on, and got this whole stream of great undergraduate research projects, changing binary to ternary, changing contiguous to non-contiguous, and changing avoid to contain. And it's just changing one word at a time that inspired each of these. And so what one word at a time might I still change here? Well, I told you about very specific trees at the beginning. You already saw me change binary to ternary with one team of students. But why do the trees have to be ordered? Why do they have to be rooted? Why do they have to be full? What happens when you get rid of some of these restrictions, or maybe look at graphs that aren't trees at all? I also told you about 2 different kinds of patterns, contiguous and non-contiguous. What if there's some sort of hybrid pattern? Or what if you can think of some other kind of pattern, like inspired by my first slide? All the e to the power x plus 1 trees were in the bottom of the tree. What if you have some special restriction on where the pattern has to be within the larger tree? those things are wide open. And I would encourage you to experiment. As an enumerator, one of my favorite ways to find problems is not just change a word, but I can always get brute force data by making the computer generate examples, and I can go, this sequence looks nice. I'll see if undergrads can figure it out. This one looks messy. Maybe we save that for later. But there's a world of problems out there from just changing one word at a time. If you'd like to learn more about these particular projects, I recommend these references, and thanks for listening.
Hooray! Thank you, Laura. Let's give Laura some love in the chat. This was a fantastic talk. You're making me want to think about pattern avoidance in non-tree graphs. That's awesome. So if you have a question for Laura, you're welcome to put it in the Q&A or the chat. We'll find it. Any questions? So we're seeing a lot of clapping, thank yous. I don't know if you can see this. Do you have two screens going, Laura?
Yeah, I do.
Okay.
It's been my winning strategy for the last year.
That's awesome. All right. I'm not seeing any questions yet, though. You're big in Minnesota.
Well, Jennifer's a friend.
That's awesome. Cool. So our next speaker is Amanda Harsey, just to let you know where we're at. And she will be giving a talk in about 9 minutes, but you are welcome to chat. In fact, if you want to hop on here and share your video and your audio and talk to Laura in person, I mean.
And I see I did get one question in the chat. Jennifer asked, can you extend these to other graphs, not trees? I haven't put much thought into that yet, but it is on my open problems pile. So I suspect you can extend definitions of pattern to non-trees. So then how general do you want to be? Do you want a specific family of kinds of graphs, or do you want just all graphs? This is probably more interesting if you have a specific kind of graph, kind of like trees gave us some structure. So then what kind of family of graphs sounds fun to work with? That would be my reaction there. So open problem as advertised. I can stop sharing those so Amanda can.
Okay, I just refreshed my page, so I was gone for a minute. I guess I'm not interrupting anything.
You're just fine.
All right. Well, thank you so much, Laura. Always a pleasure to hear you talk about patterns and trees. Always very inspiring.
Thanks.
Question for you, actually, before you go. I've always thought graphs are very cool, but I don't know like any of the background that you would need to know to get started in problems like this. For someone who is maybe branching out of their initial sort of research area to do research in another area of math that's more accessible for undergrads, do you have any advice for how to learn for the mentor, what you would need to learn in order to kind of know enough basics to really get started?
So I honestly don't think of this as a graph theory problem. I think of it as an enumeration problem because I'm not a graph theorist. I'm an enumerator. And so I usually think of patterns in permutations. Right. I think you need the definition of the object that you want to think about patterns in. Mm-hmm. And so if you have a well-defined combinatorics object, then make a definition of pattern and go nuts. That's my advice.
So here's something I've run into. That's great advice. One time I introduced a definition for something graph theoretical and made up my own word for it, and then discovered later that it was an actually existing type of thing that was called something else. And so when you don't know kind of what to search for when you're maybe you think you're inventing new mathematical ideas, any advice for how to I guess not duplicate some result that's already out there, or just how to figure out what's already out there?
Sure. I guess my advice is talk to people, whether it's making a presentation and you learn something new in the Q&A, or it's, okay, I'm starting to play with combinatorics. I'll go ask a friend who thinks about combinatorics, and it's a lot of networking if you're not finding it by searching on your own. I guess I had a help by the beginning of this train of talks was a talk by someone who had done the literature search in the area to get it started.
Right.
But if you don't have that, then it comes from talking to people.
Great. Good advice. All right. Well, thank you so much, Laura. If anyone thinks of questions for Laura after she's kind of offline here, you're welcome to type them in the chat or the Q&A. And I'm guessing she'll be sticking around for at least a few minutes to answer any questions that come to mind. Amanda, good to see you.
Yeah, I'm glad to make it here. I was in a mini course, and so I missed most of the session. I was really disappointed. I wanted to come for more of it. So.
Oh, that's okay. We understand.
Yeah.
Will you try and share screen and make sure everything works?
Yep. Everyone see that, and everyone can hear me?
Yep.
Cool.
Well, at least I can. And one thing that I like to have people check is, can you see your cursor? Yep, fantastic. Okay.
See me playing soccer. Sneak preview.
Wonderful. That's great. Thanks, Brandy. If as you're seeing these talks today, if you have more general questions about undergraduate research, about choosing problems, about managing groups, about being the best mentor you can, especially to students from underrepresented groups, I encourage you to bring those questions to Pamela Harris's talk for our Sigma on undergraduate research. Her talk will be at the beginning of our business meeting on Saturday at 10 a.m. Mountain Time. Should be a really good talk. Let me look up the title is Using Restorative Practices to Build Research Communities. So she'll be talking about that, but I'm sure she and others in the audience will have lots of great experience and can answer questions you have if you're just kind of new to undergraduate research, a new mentor. We'll have a wealth of expertise in the room there. So that'll be a great thing to come to. Of course, Amanda, I'm sure, could answer lots of questions related to mentoring undergraduate research after her talk as well.
Yeah, I do have some like recommended reading of like some articles that are good about like organizing undergrad research and stuff. So I kind of have my talk as like a little bit of background about me, some gateway drug, linear algebra based force analytics models that you can get into, and then some sample student problems so you can kind of get an idea about that, and then some general advice about like doing undergrad research and getting started, how to recruit students and find funding.
Oh, that's fantastic. Thank you.
So that's the plan.
And for those of you who didn't hear my plug earlier about FIRM, it's a book series, Foundations of Undergraduate Research in Math. Brandy gave us the link and I'm reposting it here. It's a book series published by Springer where the chapters are kind of self-contained descriptions of a research area that's accessible for undergraduate research and gives you the background information that you need to know in order to get started in that area, all the references that you should be familiar with if you want to do research in that area, and then open problems that are accessible for undergrads. So that's another great resource. And there are 2 volumes, I think, that will be coming out in the next year or 2 that are specifically problems that are accessible for students with less math background. So maybe just calculus math background, or maybe not even that. So if you're interested in that, especially if you're a professor at a community college, want to work with students that have sort of less advanced math under their belt, that's going to be a great resource. Okay, I think we're just about ready here. So Amanda, I think I might have met you in a van on our way to or from a Pick Math workshop where we were learning about data science-y stuff. I'm really excited to see that you are working in this area with undergrads. Very happy that you agreed to speak in our session, and I can't wait to hear what you have to say about sports analytics. So please take it away.
All right, well, thanks. As she mentioned, I'm Amanda Harshey, and I'm going to talk about some open and accessible problems in the realm of sports analytics research. I'm going from a very very basic, people who may not have any background in sports analytics. So hold on. So a little bit about me. I played college soccer, so I really like sports. I got my bachelor's in mathematics from Taylor University, which is a liberal arts school in Indiana. I graduated with my PhD from IUPUI, and my dissertation area was geometric group theory, so very, very far away from sports analytics. I'm currently an associate professor at Lewis University, which is a teaching-focused school with a little bit of research expectations. When I went to grad school, I kind of had the mantra that I will stay in grad school until they kick me out. I definitely did not consider myself like a really good researcher at all. I considered myself a good teacher. So my goal was always like, I'll look for a good teaching school with little research expectations because I'm not good at research. And I got that kind of feedback all throughout my grad school experience. So I was definitely not someone who was like, yeah, I really like research, and I feel very confident in that. So I got hired at Lewis University. And one of the things about this group of people at Lewis was that the rest of the math faculty had been there for over 30 years, and none of them had done any research with students. And so one of the goals when I was hired was that I would help Lewis start getting students involved in math research. And so that was kind of I definitely had some problems with geometric group theory that I could do, but if I was supposed to kind of get students really excited about math research, I was like, oh, how, maybe I need to kind of think about some other problems. So what I did was I actually pivoted completely. I haven't done geometric group theory since I was in grad school, and I have 3 research projects that I work with students. One is in sports analytics, but I also do research in graph theoretical modeling of self-assembly DNA, and I also do educational research. So that has really helped me be able to work with a lot of students over the years, and since 2015, I've worked with over 40 students on independent research projects. And it's been a lot of fun. And it was something that I would have never dreamed that I could have done when I was in grad school. And so one of the questions is like, why sports analytics? Why did I start to kind of think about that? Well, there's a ton of interest. Like students are always very interested in looking into this field. I was an athlete, so I really like kind of the realm. And there's just general interest. I also really like that you have a lot of questions that you can ask. So even if something's been done with one sport, you can see if it works in another sport. If it's been done at the college level, you can see, does it work at the professional level? And so you can kind of customize a lot of questions to be just with a different data set. Does it transfer to a different sport? I like that negative answers are results. Like if you're like, hey, does home versus away make a difference? And you're like, no, it doesn't. That's still a good result. I also really like that, at least like with some of the models that I'm going to talk about today, which are very basic, you can start with minimal background with just a little bit of basic linear algebra. Although I will say that having some programming experience is helpful. So one thing I want to mention is I am not a leading researcher in sports analytics research. I think Tim Chartier does a lot more with this, and he has some really great literature out there. And he's actually similar to like what Laura said, was that like I saw a talk by him and it really motivated me to kind of like think about some of these types of problems. And another thing is that like my focus has been primarily on undergrad projects. And so I'm more student focused and not really like looking to always publish all of these, projects. And I also make sure that students like ask their own research questions and they pick their own data sets. And most of the time they even pick their own research methods. And so I really let it be student driven, which I think is really great, but it also can be a little bit, kind of crazy at the beginning when you're trying to like figure out like what would work well. But I'm going to talk a little bit about different projects and give you some advice on that. So my goals for this talk are to provide you some background for a few very basic sports analytic models that are based in linear algebra. One of my professors in grad school said that when you're wanting to work with undergrads, having problems that only need linear algebra are really great because students can take linear algebra pretty quickly. I'm also going to provide some examples of some real student projects and give some resources and advice for getting started. But I also kind of want this whole talk to be just kind of an encouragement for people who are newbies, because if I can do it, who had like no background in this, you can definitely do it too. So here are a few of my favorite, what I like to consider gateway sports analytics methods. They're a way to get you kind of started, and then you can go off from there. So one of the common problems that we can look at is ranking teams, figuring out who's number one or how is the end of the season going to go. And so one of the most basic ways to do ranking of teams is through win percentage. The rating of a team depends on the number of wins that they had over the total games. And sometimes that's really easy. So this is something that Tim Chartier calls the poor sportsmanship model, where the team that wins, so we have this little directed graph here, points to the team that they beat. So in this case, A beat all the three teams, D beat B, but lost to A and C. So when you have something like this, it's pretty easy to kind of use win percentage to be able to rank them. But you can immediately see that when you start adding more data and more games, things get a little bit more difficult to be able to figure out who's actually number one. And so there's definitely some disadvantages for just using win percentage. You have things like, winning 2 out of 2 games is the same as winning 100 out of 100. It doesn't take into how much you won by. You may want to know, like, hey, did a team win all their games at the beginning of the season, but now they're losing as we're getting close to the tournament? These are all things we would kind of like to know. And luckily, linear algebra can help us. And so these linear algebra models can help. So one of the first models that we're going to look at is just a slight modification to win percentage. So this was developed by Dr. Wesley Culley, and he uses Laplace's rule of succession to just slightly modify the win percentage. And what's nice about this is that an untried team, instead of having 0/0, now has a half or a 50% chance of like winning, or kind of their win percentage. And he also incorporated strength of schedule. And what he did here was pretty neat, I think. So if you look, and this is a kind of our rating for our team, and we have our total number of wins over the total number of games. He multiply both sides, do a little bit of algebra. We split the WI into WI over 2, WI over 2, and we add 0. And now we have this new equation. And what we do is we take this term right here, which is the total number of wins plus the total number of losses divided by 2, and we approximate this value by the sum of the ratings that our team has played. And so here's an example of how that works. So here we have A. A has played a total of 3 games, and so TI is 3. They have won 2 games, so we have our WI is 2, and they lost to C. And we add the total number of the ratings of the team that they played. They played B twice and they played C once. And so we can kind of put this together and set up a system of equations, and we can solve this system of equations. Now, what we get when we solve this is we get a rating vector. And what we do is we take the rating vector and we take the values for each of our teams, and we come up with a ranking by ordering them in the order of their rating. Okay, so in this case, we would rank team A first, then C, and then B. Now, this is a nice model. One thing I want you to notice is that it was a symmetric matrix, so it's a nice thing to solve. It's a little harder to set up. But it incorporates, strength of schedule, but doesn't incorporate score. The other model that I'm going to look at is the Massey method, and this is this actually uses scores to be able to set up their system of equations. So this is an easier way to like set up a system of equations. So in this case, we just say that the difference between the two ratings of a team is just by their score differential. So team A beat B by 5, they lost from C by 17. And so you can set up this system of equations. But we have a problem here, okay? A lot of times when teams play each other more than once, we aren't going to be able to have the same score differential. So we know automatically that we're not going to get a solution for this. This is going to be an inconsistent system. And so what Massey did was he used least squares and set up the normal equations to be able to solve this. So here's what our system looks like. And we multiply both sides by the transpose. And now we get a system that has a solution, but we have another problem now. Now the problem is that we have infinitely many solutions, and we don't want to be able to say, well, there are infinitely many ways to rate these. So what Massey did was he added a row that was not a linear combination of the other rows. In particular, he adds this row, which is all ones and zeros at the end, which is basically that the sum of the ratings of the teams equals 0. Now you can pick any type of row here as long as it's not in the span of the other rows, but I kind of like this one, and this is what is traditionally used. So when we do that, we now get a new system which now has one solution, and we do the same thing that we did with Coley, and we put them in order depending on their rating value. So in this case, the rating is C, A, and B. And so you can see that, both systems came up with something different. And you may be asking, okay, this is great, Amanda, but like if we all just use Coley and we all just use Massey, we're just going to have the same ratings. Well, this is where you can really kind of do a little bit of playing with it and research with it. So this is what I often have some of my students do. So you can incorporate other factors of the game by weighting different like games. So for example, I may want to look and say like, hey, if a team wins on the road versus at home, I want them to get kind of a bump. I want them to kind of have that win count a little bit more. You can do something where you want wins later in the season to count more than wins at the beginning of the season. You can kind of give an extra bump if they won a conference game. And so this is where students can really kind of pick what they want to kind of play with and modify these methods by just adding these like coefficients in front of our kind of games and our ratings, depending on each game. And so one thing I do want to mention, and I think it's interesting that Allison was like, hey, we met at the PIC math data analytics research workshop, is that I am putting one of those slides from there, because one of the things that when you're looking into sports analytics, you're looking at kind of predicting the future. And one of the common things that you want to be careful about is kind of overfitting. So for example, if I have a data set from the year 2017, I can make a model that works really well for that data set, but in general, you kind of want your model to work well for other years, not past years that has already happened. So one thing that you can do is you can use cross-validation to help this. So like a lot of my students will incorporate this to kind of help them kind of mimic what they would actually want for a prediction. So what they do is they take their data set and they will split it into a training set that they kind of make their model a cross-validation that we then test, and then kind of go back to our training and test again and go back and forth. And then we have another part of our data that we use for a final testing that we kind of keep hidden until the end. And so this is a way to kind of mimic what would actually be happening in real life when you're actually like trying to come up with a predictive model that will work beyond just your data set. And so that's something that a lot of my students will incorporate. So now I want to talk a little bit about some of the student projects that we've had, so that you can kind of get some ideas of like, hey, this is something that I could easily do. And again, I mentioned that, you can kind of pick any sport. And that's what's really great about this field, is that you can pick different data sets. And so it doesn't, I feel like it's easy to be able to do something new, because you can always look at a different team, you can look at a different sport, you can look at a different data set. And so one of my early projects was with Carly. So Carly was a softball player and she wanted to use the Coley method. And so she trained on 80% of her data and used 20% for cross-validation. And she looked at kind of some of the weights that I already mentioned, kind of like short, long, normal games, home, away, early, mid, and late season. And what she found was that weighting the middle part of the season yielded the best results. After her, I had a basketball player named Marco who added more data to Carly's project. He combined and tested various weights and factors. In particular, he kind of automated it a little bit better. And he also incorporated something that I'm not going to talk too much about, but he incorporated something called principal component analysis to kind of look and kind of determine which individual statistics were useful for rating these teams. And so he incorporated that into Carly's project. Another project that I did, this was probably my first sports analytics project, was with a bunch of golfers. And in golf, each day they drop the worst score of the day. And so we wanted to know, if we incorporated that back in, would it be a better predictor? And maybe if we weighted different scores depending on the golfer, maybe that would be more predictive for end of the season. And so they used the massing method here because it was like more score based. And one thing I want to mention here is that, like, we were actually doing this project as the season was going, and we attempted to use cross-validation on, like, we were going to train on the first 3 tournaments and then use cross-validation for our 4th tournament. But what happened with the 4th tournament is that it got rained out, and so it was kind of an outlier. So that's something to kind of, I guess I would say, maybe don't do. One lesson is maybe don't do data from the current season as you're like working on it. They did find some little bump for like incorporating the drop score, but nothing to get all hot and sweaty about. After that method, or after that project, I had 2 students, Adrian and Brandon. They wanted to incorporate a neural net into this project. And so they converted our project into Python. And one of the things they found was that no weights was best. And I'm adding this here because this was a project that didn't really work out how we were hoping for. We didn't have enough data to really make it, but it was still very worthwhile for them because they learned a lot about writing things in Python and putting things into a neural net. So even though it may seem like, oh, we didn't really get that great of results, it's still a great project for them, and they were still able to present and learn a lot from it. And it also helped because then Kevin had the program in Python, and he was a great Python programmer, and so then he was able to extend on it. In particular, he found that like the best predictor for the model was if you incorporated some type of course length. He also used a different type of cross-validation, a nested one, that as you kind of are adding more data, you can kind of keep splitting your data set into kind of the test and the train and the cross-validation. Finally, I also have, I had Megan and her group. Now I'm allowing students to kind of decide what model they want. And they said, we want to explore baseball and we want to do Markov chains. And so they wanted to know if win streaks actually help predict. And so what is a Markov chain? So a Markov chain is a process with the probability of a system and being in a particular state depends only on the previous state. So this is used a lot to model movements of board games and population changes. How you kind of represent this is through a transition matrix, which will tell you that, hey, if I'm moving, the probability of moving from state 2 to state 1 is 30%. And so the idea is that over time, if we keep doing this over and over again, what's kind of the probability of being in each state or each team? And so what we often want to do is find the steady state vector that represents this kind of like end of year, end of time probability of being in a state. So what they did was they modified a previous model by Kavam and Sokol. They came up with kind of this probability matrix to be able to define the transition states, and they found that win streaks actually worked well for the top teams, but not for the conference as a whole. So I know I only have a few more minutes left, so I want to make sure that I get to this part too, because I think one of the things about getting started in research, and if you're someone who hasn't done it before, I want to say, don't be afraid. Like, I had no experience in sports analytics research, but you can definitely get your feet wet in this. Another thing, this is true for all research, everything takes longer than expected, especially data collecting and cleaning. I always recommend starting on a smaller set and then kind of expanding off of that. And you might need to make a slight adjustment to your research questions as you go. I think it's important to meet regularly with your students and set expectations. And I always require a deliverable, so like some type of like report or project or poster. And don't be afraid to ask, I think as Laura mentioned, to ask help from peers. And finally, it's very difficult, this area, because prediction is very difficult, especially if it's about the future. Some recruitment advice. So how do I find students to work with? Sometimes I directly approach and ask them. I usually try to talk about like doing any type of math research so they don't feel pressure to like work with me. I also send regular emails talking about the importance of research, research opportunities and jobs, and RU prep to students, and that often gets people excited. We also recently started a math research course so students can get credit for doing math research. And we've also run some special topics in research areas. And finally, if we have a senior capstone course where they have to like do a little bit of math research. So having, sometimes I can say like, hey, if you work with me, you can then use it for your senior seminar project. So that's kind of a nice way. That's what happened with Sheila in the previous project. So how do you fund the students? So one of the things that you can do is you can look for internal grants. You can ask your chair, dean, and provost. They often have extra funding. Sometimes if you have a group of faculty, you could maybe start an internal summer undergraduate research. There's the KERM mini grant for the Council of Undergraduate Research in Mathematics. There's the NRU Up grant, which can get you started on like a mini REU. The MAA Sports Sigma group has funding for data sets and for conferences. And you can also look at local researches or local businesses to kind of see if they would be willing to fund you. As I promised earlier, like here's some really good resources if you're looking for tips about like mentoring undergrad research. And also I added When Life is Linear by Tim Chartier, which talks about some of these methods. One final little thing I want to mention is that another really good resource is the ROOF program. If you're looking to connect with other teachers or people at more teaching focused schools to work on undergraduate research projects, that's how I got involved with my DNA self-assembly group. I also recommend maybe looking into Pick Math. They all have a lot of really cool projects and funding there as well to be able to begin to work on projects. And finally, I want to mention that the Sports Sigma is a great group to find collaborators in this area. And there's also a Math and Sports Journal, which would be really good for some of your results if you end up wanting to publish them. So thank you again for inviting me to speak, and thank you all for listening to me. I want to thank Allison and Laura and Dr. Tim Chartier for the initial motivation for this, the Sports Sigma group, the Pick Math group, and for the Puma STEM and SURE programs that help fund a lot of my students, and of course the past and present students who have worked in sports analytics with me. If you have any questions, or if I know I went through a lot of things really quickly and you want to see a little bit more details about any of the projects or the weighting or anything, please feel free to contact me. I'm also happy to share some sample grants that I've gotten in this field. So I'd be happy to, well, they're more internal grants. They're not like real big grants, but I'd be very happy to share anything. So thank you.
Amanda, that was awesome. That you just gave us so many resources. Thank you so much. I tried to put a bunch of these things in the chat. I put in a link to KERM, which is a place you can go to get a mini grant to support academic year research with students. That'll pay for part of a course release for the faculty member and will give the students a salary to work on a project. I also put in a link to the NREUP grants, another way to get grants to work with groups of students from underrepresented groups. There's a link to the book. Thank you, Amanda, for referencing our book. The book that Laura Pudwell and I wrote with Michael Dorf called, what is it called? Mathematician's Practical Guide to Mentoring Undergraduate Research. And then also, you're not the first person I've heard talk about the amazing benefits of REUF, REUF. So it's like research experiences for undergraduate faculty, great program for folks who want to branch out with their research area and get into an area that would be accessible for students. So thank you for all those resources. Do we have any questions for Amanda? Oh, hi, Jennifer. Good to see you here.
So again, like Laura said, she was just changing words. Like here you can just change teams and data sets and you have a completely new problem. And so that's one of the really fun things. I think that makes it easy to like get started in this area. And what I found is that now I'm more inclined to just be like, hey, what do you want to do? Like this summer, I'm working in differential equations. I've never done differential equation like research type stuff before, but you know, once you kind of get your feet wet, you feel a lot more confident about like, I can look at a new model and I can modify it and I can like kind of make some changes to it to fit our research problems, which I think is pretty cool.
Well, I'm not seeing any questions. It might be that people are kind of maxed out after a long day of conferencing, but thank you so much for speaking, for closing out our session today. And one last plug for the Undergraduate Research Sigma business meeting where we have Pamela Harris giving a talk about mentoring undergraduate research. And that is at 10 a.m. Mountain Time on Saturday. Thank you again to all of our speakers today. It's been a great session. I really appreciate you coming and engaging. And we will see you around the conference.